Alrighty, folks. How's it going? Welcome, everyone. Hope you all are having a wonderful day. So, I'm doing good. Yeah, this is a little early in the morning. I'm thinking that maybe I want to do these a little later in the day, but we'll see. I think I might pull the server and see how people feel about starting this slightly later. 'Cause I think maybe more people will be able to show up too. As engineers in general, I think we like to sleep in. Not completely a bad thing. Anyway, today we're going to be looking at data structures. Why are data structures important? Yeah, who doesn't want to sleep in? I love to sleep in. And I can understand why people wouldn't necessarily be here because they need to sleep in. In fact, I know a couple people are like, if it was later, I would watch. So we'll see. We'll see how it goes. But yeah, data structures. Introduction into the way we store data. Why is this important? Well, for one, and I really wish I had some Legos for this, honestly, because this is a perfect Lego example. Um, Data structures are kind of the pieces. Hmm, let's see. This user. Oh, I have my. Let's see. There we go. I'm a first bot. That's exciting. I don't think we have one of those before. And now the bot thing won't go away. Anyway, um, they're important because they're the little building blocks that work into and build into your code and your algorithms. So when you're building a complex algorithm, these sorts of things are going to be the small little pieces that you utilize to make your algorithms pop. And data structures are how we store data, right? So a lot of times an algorithm, you're not going to get an algorithm that just says generate all the data yourself, do a bunch of random crap to it, and then don't output anything. Usually you're going to get data in a certain format, and then you're going to get data out, and you're going to need to put it out in a certain format. So let's take a look at the first one of these. Oh, I guess let's say why does this matter for interviews? Well, interviews most of the time are going to be asking you to do algorithms. And that means that they're going to want you to know data. What they're going to want from you is they're going to want you to know these data structures in a very familiar way. They're not going to necessarily expect you to be able to create all of them, though it can be very helpful to create all of them. What they're going to expect you to know is how these data structures work together. And for example, in the case of like a linked list or a hash map, JavaScript already has those as native variables that you can create. So you don't need to know how to create a hash map in JavaScript, or you don't need to know how to create a linked list, for instance. But it's still useful to know how those things interact, just because you may need to have to deal with them at some point. So the first data structure that you'll probably run into, and here's the thing, when I say array in this particular context, I do not mean the JavaScript array. The JavaScript array is actually something different, and we will cover that a little bit later. We treat it as an array because we can access it as an array, but a strict array contains a list of items, right? Like a standard array. It has a defined size that it cannot go past. So when you create an array, an actual strict array, and this is more like the C++ or Java style array, you tell it, I want you to have 10 items max that you can store. And at that point, the system will allocate memory for that array. And this is the difference between like a JavaScript array, we can push and pop, right? Many languages, like the very low level array, you cannot do that. You have a certain length of data that you have available. It is indexed by positive integers. You can't negatively index an array in most languages. Some languages do let you access an array by negative index, but what that will actually do is that will start at the end and go backwards rather than starting at the beginning and going forwards. Strict arrays can only contain one type of data. The reason for that is when you define an array, a strict array anyway, the system allocates a certain amount of memory for it based on the type of data you're storing. So if you are storing a type of data that takes up 3 bytes, for instance, the array will allocate 3 bytes times however many elements you have. So if I said I had a number, right, maybe a 32-bit number, and I want 10, the system is going to allocate 40 bytes of memory for that. And that's just because that's how these systems work. They want to be very memory efficient, and they need to work that way. So here's an example of a strict array in memory. It's of size 4, which means the system has allocated 4 memory slots to it. In this case, I'm just using an arbitrary slot for memory. You could assume this is like a byte of memory. So 0 has the first element of the array, 1. Second has the 5th, and you can see this is why we zero index arrays, because memory starts at 0. 2 has 23. 3 is null. Now you might be thinking, yeah, but there's only 3 elements in the array. Why do you need this 4th one down here? Well, because in a strict array, a true array, as soon as you tell it to be size 4, it allocates the memory for it. Even if you're not putting anything in here, it will allocate that memory and hold on to it. And so now you can see why an array, if I access the array and I say, oh, memory address, give me the first element. Well, the array knows at what memory location it starts. And so it says, oh, I'll just add your number that you gave me to whatever my memory location is, multiplied by the size of what I'm dealing with. And so let's say we've got 4 bytes per memory location. This would be 16 memory addresses. If I wanted the second one, I would take, 1, because 1 is that second one. And I'd say maybe I start at 0. I'm going to add 1 times 4. And so my first memory address is going to be 4. And then I just read 4 bytes out of that. And this is why arrays are constant time lookup. They can look up immediately. They're also constant time set. Because if I want to set this 4th position, for example, I want to put 5 onto the end of the array, I know immediately what memory address that is because I know how big my array is and I know how big my data is. It's just a very simple algorithm that tells me what memory location that data needs to go into. Let's see. And so let's say I wanted to remove the element at index 1. Well, you notice it doesn't collapse that. I just deleted, I set it to null. But these don't shrink backwards because that's not how strict arrays work. They have that same memory address. If you want to actually move all these back, that's an O of n operation because you have to loop over the whole array and manually move all the elements up. Strict arrays, you're probably not going to work with that much, to be honest. And languages like Python, like JavaScript, PHP, their arrays don't behave this way because they're technically linked lists and not arrays. They're actually technically something else, but we'll get into that. This is more if you are working in Java or you're working in C++ or you're working in some of those older languages that didn't have those data structures when they first came out. On the other hand, Java and C++ do have the ability to just create linked lists. It's just a little bit more painful to work with them. So a strict array, it's still good to know because let's say your interviewer suddenly tells you, hey, you're going to have to work in Java for this. It's important, first of all, that's not a very nice thing for them to do. And they shouldn't do that. But I feel like I just got a message about something. I did. Yeah, that's not a very nice thing for them to do because you don't know Java. But if they do, then just something to bear in mind there is the array in those languages is not the same as the array you're used to. All right. I'm not really going to go through and code this one because this is a very low level system array. Like you don't really need to worry about it too much. It's just I brought this up just to let you know that like JavaScript and a lot of the languages you're going to use, the more modern languages don't use this implementation. They use some other implementation, but it's important to be aware of that so that you know how it's working under the hood. All right, so let's take a look at the linked list. So the linked list contains a list of items similar to the strict array, but it can expand infinitely by adding new items. It cannot be easily indexed, and when we go over the implementation of this, I'll show you why. It can also contain any type of data. Now you notice this also does not sound like a JavaScript array. A JavaScript array can expand infinitely, but it can be indexed easily. So what gives? Well, JavaScript arrays and by extension PHP and Python arrays technically also are not linked lists. They behave a lot like linked lists, but you'll see in a little bit why. And it's this indexed part, because a JavaScript array, you can index it. You can say, okay, get me the third element, get me the fourth element, but you can also infinitely expand it. That seems kind of weird, right? So a linked list, this is it. So I've gotten, you see now, a little bit more complicated memory address here. Let me, oh no, this is fine where the camera is. So this is a linked list containing the value 5. Now you notice we've got specifically 2 memory addresses here, 1000 and 1001. 1000 has 5. What is 1001? Why have we allocated? Why have we put something there? Well, let me move on to the next slide and maybe you'll see why. So if I add 10 to that list, I push 10 onto the end of that list, okay? We still have 5, but now this has changed because now we have 10. Why didn't 10 go in 1001? Well, this is the beauty of the linked list. The linked list contains 2 items. One, it contains the value, or if you're in a language like C++, the pointer to the value that you're trying to store in the list. It also contains the memory location of the next element. And that is how it's able to grow infinitely. Because let's say I created another variable at 1004, right? Well, I can't use that anymore. So if I add another item to the linked list, I'd have to put it in 1005. And so that's why then this pointer basically tells you, hey, where's the next place in memory that the next value is? This is very different from the array. Because you saw the strict array has a block of memory and it says this is the only memory I'm allowed to access. A linked list, on the other hand, creates nodes, or I guess elements. It depends on your terminology you want to use. But it creates different objects in memory that could be anywhere in memory. And it just knows where to keep them all together. And it's almost kind of like a centipede. All of the segments are linked to the segment ahead of it. A segment in the middle of the centipede doesn't know where the head of the centipede is. A segment at the back of the centipede knows that it's the back, but it doesn't know where the front is. It doesn't know where the middle is. It just knows the segment in front and behind it. So there's a couple kinds of linked lists, and we'll talk about those a little bit. So let's say, well, let me go back here. Let's say we want to add another element to this list, right? We would start, because our memory is empty, at 1004. Okay. So we move forward. I'm adding a string at this point because linked lists are not type bound. Whereas if you have an array, you can have a certain type of data in there. Also, if my audio is off, someone please let me know. It looks okay on my end, but I just want to make sure. So I've got my H here. I've got my I. These are the 2 characters of the string, right? And then I've got this null terminator that lets the system know the string is complete. Don't worry about that too much. I just, in case I have any C++ purists in here, I wanted to make sure that they were happy with this. And then we've got another null. That's the next address. Well, it's not set, but we still need to allocate the memory for it because we still need to have a variable set up. Now, if I'm looping through this list, first of all, I would hit the first array, or the first address. I would say, okay, there's the value. I'd look at the next one. I'd say, okay, the next one is at 1002, and then I jump there. Okay, that's the next value. Now this one is 1004. You notice in this case, these addresses are right after each other, but they don't have to be. And that becomes really important because as your program runs, the fact that these don't have to be next to each other is really valuable because it means you can allocate other memory in between them and the list still flows as if it was a normal thing. So what I'm going to do now is I'm actually going to give you and show you what the code for a linked list would be. Okay, so let's actually just make a class. The first thing we're going to do all right, is I'm going to create a node class. Okay. And let's see, do I have to put, I haven't done classes in JavaScript for a while. Do I have to put instructor? I think I don't have to put function in front of it. I guess we'll find out. So then this dot value equals value, this dot next equals null. This, so far, is fairly similar to that data, right? Also, I'm just realizing this freaking thing is right in the middle of the band thing I have is right in the middle of the chat. So now I can't see the chat. Give me just a second. I'm gonna try to see if I can get rid of this. What if I pop it out? No, if I pop it out, that doesn't help me at all. Docs menu in the menu bar. Oh god, now it's everywhere. All right, now everything is gone in places I don't want it to be. There we go. Okay, cool. Yeah, now I can see everything fine. All right, so sorry about that. Anyway, the node here has a value, right, which we saw, and then it has a next pointer. This will tell me what is the next element. And because you saw on that linked list, right, each element, oops. Oh, I guess I went over an example. Okay, well, let's look at the last example then, because apparently I skipped it. All right, so now let's say if we were to remove that element, the second element. Now you can see I didn't move this up. I updated the address that's pointing to. So now if I was to loop through this, I can go 5, and then I know 1004, and I jump right here. And now this memory is free to be used by something else. So this is a property that linked lists have. If you remove an element, it actually pulls it out of the list and seamlessly everything flows through, which arrays don't have because they have that specific memory allocation for it. So yeah, that's everything for that. So yeah, so you can see that the fact that we have these objects, you can always, yes. Well, no, you can't, at this point, you can't jump back to 1002 because it's been lost to memory. The linked list no longer knows about it. So if I insert another element, maybe it will be inserted at 1002, but at that point I go to from 1000, 1004, and then I jump to 1002. And the system under the hood takes care of all this for us. But what this means is we have the ability to remove and add elements very flexibly. We can also even remove and add elements from the middle of a linked list, because all you do is you just update these pointers, right? And that works. So that's kind of why linked lists are really nice. The thing is, they do take up more memory because you have to allocate another memory space to this next address. And in fact, if you have a doubly linked list, you have to allocate 2 memory spaces. And that is what JavaScript does. Well, actually, JavaScript is doing something different, but that is what a lot of implementations of arrays do under the hood, is they're just taking that extra memory hit. And that's why a lot of the more modern languages are a little less memory efficient, because they are using these more complicated data structures under the hood. All right. So back to here. We have, why is moving? Because, well, for one, if you were to move that code into there, you don't know if it's gonna fit, for one. I guess let me see. So let's say I put this in here, right? I've got 4 memory addresses here, so I could shift them back by 2. But what if I was deleting this and I wanted to shift something that was 2 memory addresses? It's very expensive, and the other issue about it too is that most modern languages don't actually give you that kind of fine manipulation of the memory space. Even in C++, you can kind of get around it if you allocate a bunch of memory yourself as like a heap memory and then do the memory manipulation on your own. But that overrides a bunch of what the language is doing for you automatically. Basically, we don't need to fill these up, because as far as we, the developer, are concerned, that memory, we don't even know it exists. it's not something that we need to worry about because we just know, oh, I've got 2 elements in my linked list. And actually, I should probably get rid of this here. I've got 2 elements in my linked list. I've got one that has 5, and I've got the other that's got this string. I don't care about the empty memory because I don't even know it's there. There may be gaps, like, and this is just an example, right, of here. This stuff may be like 2002, right? That is equally possible. That these could be somewhere completely different in my memory space. And the whole point of a linked list is that it ties them all together in a way that I don't need to care where it is. So now in this case, I'm going from memory location 1000 to memory location 2002, and then all the way back to memory location 1004. At that point, there's a gap of like 1,000 memory locations in between those elements. But then I come all the way back to this one because maybe there's 2 other elements. And there's a whole very complicated system that's running under the hood of all these languages that is figuring out what memory it has available so it can allocate it appropriately to variables. That is not something we necessarily want to deal with. If you really want to do that kind of work, then learn C, not C++, but C, because C lets you do some really, really powerful low-level memory manipulation. I guess C++ does as well, but C is just like, you have to. So it kind of forces you to. The thing is, most languages since that point have been attempting to move away from that. So stuff like the garbage collector in JavaScript and Java and most modern languages, that didn't used to exist. It used to be a real pain. You get dropped memory all over the place. Like, have you ever heard of like a buffer overflow error? That will happen because someone allocated a normal array and then accidentally indexed something that was too far on that array, right? And that can't happen in JavaScript because it uses more safe data structures. And yeah, so basically the long-winded thing here is that we don't want to have to do this memory manipulation. We don't want to have to do this because it really makes your code 1,000 times more complicated. And I just want to show you under the hood how it works because it's valuable to know kind of what this is doing. So you say like, okay, why is a linked list set up the way and why does it have the limitations? Because the thing to notice is linked lists, right? We cannot index. So we can't say linked list bracket 2 because, or rather we can, but that's an O of N operation because we have to loop through the entire array to get to that point. We can't just compute the specific memory location it's at. And so that's why if you do have a linked list and it is a true linked list and you try to get a value at a certain point, it's going to be expensive. And that's just something that you have to keep in mind. Again, that's why this is not actually technically how the JavaScript array works. Because the JavaScript array can do that very quickly, but also can expand infinitely. And we'll talk about that a little bit later. But yeah, so the linked list, very, very interesting data structure, very common, but also most modern languages just deal with it. But also an interviewer may want you to know how it works. So we start off with a node, okay? Nodes basically have a value and a pointer to their next option, their next operator. Then we have our linked list, okay? And what the linked list has is it has a tail, a head and a tail. Now, what does it do with the head and the tail? Well, if you think about the centipede again, or like if you ever played Snake, you have the head and you want to start at the head to loop through. But when you're adding new stuff, you want to add them to the tail. So we need to know where both those things are, okay? Equals null. So they start off at null. And that's not particularly very interesting, right? So if I was like, oh, yeah, you know, list equals new linked list, and I, you know, spelled it correctly. Let me just make sure if I run this. Okay, I did my classes correctly. So it doesn't do anything. But now let's do an insert function, actually, because I've been a class. See, I've been writing entirely too much PHP recently. Value. Now, insert is going to add, well, let's actually do it as push, because that's what it's technically called. Push, you should be familiar with this from JavaScript, adds an element to the end of the list, right? So what are we going to do with our push? We have our value. First thing we need to do is we need to create a new node, right? New node equals new node with the value. So now we've got our node. Now we basically want to push it on to the end unless we have no head and no tail, unless the list is empty. So if we have no head, then we just say, okay, well, the head is now the first node that we inserted. Equals new node. Okay, that's totally fine. All right, that makes sense. So if we have no head and no tail, well, then the head and the tail are going to be the same object. And that's the case. If you had a snake, for instance, with one segment, or a centipede with one segment, that's its head and its tail, technically. So now that we've got a push, well, let's say list.push, push 5. Okay, let's push a couple values. Push 10. Okay. Now we actually want to print out. So let's do like a dump of our list, okay? And I'm just going to call this iterate. And I'm going to give a callback because this is Java. So how we iterate over this, well, first of all, let's just do this on this .head to start off with, okay? So we're going to say list.iterate element. And let's actually, console.log element. Okay. Now if I run this, you can see I get my node value of 5. Next is null. Okay, that's great because that's the first element that I pushed onto that list. Now, if I push another node, you can see it kind of just ignores it. It's like, yeah, whatever. That's cool, but I've already got my head. So in this case here, well, if we already have the head set, which means we already have a node that exists, we're actually going to push it onto the tail. And the reason for that being, let's just get paint up, I'll show you. The reason for that being, let's say if we have, right, our head element here, right, and if our tail is pointed at the same spot, well, the next time we want to add a segment, we want to add it here, and we want to have it pointing to there. So this becomes the new tail then. And then we add another segment, and it points to that tail, which points to this tail. So now this is still the head. Oops. Here. So if we want to loop over this now, we start with the head, then we move to the next, then we move to the next until we can't go any further. And that's how we iterate over the linked list. So at this point then we need to add this onto the tail. So we have our new node. So we say, okay, this .tail.next equals new node. All right, we're setting that next pointer to say, here's the next node in the chain. But then we have to advance our tail along. This .tail equals new node. Okay. So if I run this now, it says, oh, yeah. We have our value 5. Our next is this pointer 10. Cool. I kind of want to just pass the value into this callback, though, so I don't have this whole complicated data structure coming through. 5. So now I want to iterate over it. So I'm going to do this. I'm going to say current equals this .head, while current is not equal to null. We're going to call the callback on current, and then we're going to advance current equals .next. This structure here is a very common one in data structures, especially when we've got this list of nodes and they're somehow connected to each other. The ability to advance, kind of keep that current pointer, but advance along a chain, because we don't know how many elements there are necessarily. We can't really do this in a for loop. Well, we could keep track of how many elements there are. That is a thing that some linked lists do, and it is kind of a nice thing to do, but this is just kind of nicer. All right, so now if I run this, you see 5, 10. Okay, let's say I push another element in. Let's push a string. There you go. It doesn't care. So now you can see this is starting to look a little bit like a JavaScript array, except we can't index it very well. We can't really get an element at a certain point. So let's try to delete something, right? Let's add a deletion method to like pop. Okay. Well, pop is going to remove from the tail, right? And that's in a standard linked list. You push and pop, and that's from the end of that list. So if we pop, okay, we're gonna say if not this dot tail. Well, then we're just gonna return null because there's nothing to do. Otherwise, okay, we're gonna say we need to value is going to be this dot tail dot value, okay, and then we need to de-advance our tail. Now the problem is we can't really do that very easily because our tail doesn't know what came before it. It only knows what came after it. This is what's known as a singly linked list. And the singly linked list, these arrows, these are one direction only. And it goes this way. Okay? The head knows about what comes after it. This knows what comes after it, but the head doesn't know about this, and this doesn't know about any of the rest of the array. No idea. It has no idea how to get back to these. So if we want to be able to actually pop as well, we need what's called a doubly linked list. And a doubly linked list is where those arrows are bidirectional, where something knows about what came before it, and it knows what came after it. So a doubly linked list also takes up another whole section of memory because it needs to store that pointer as well. So if we go back, we go back here. If we want to make this a doubly linked list, we'd also need a previous pointer. So elements would need to know what their previous pointer was. So now when we're inserting a node, we're saying, okay, you know, this dot tail dot next is new node, but we're also saying new node dot previous is this dot tail. So we're hooking up that double arrow. This one here is that first arrow that points forward. This one here is the second arrow that points backwards. So now if we have our previous pointer, it means we know we can look backwards. Now we can say this dot tail equals this dot tail dot previous, and we can rewind. And then I can return value because that's what you do when you pop. Okay, so then let me grab this, and then let's list.pop, and then we'll iterate over it again. Okay. Oh, that did not do what I wanted it to do. Because it gave me the same list over again. This dot tail. Oh, because yeah. So then I say this dot tail dot next equals null. So I have to sever that pointer because then it gets garbage collected. And now it disappears. So yeah, so this is now a doubly linked list. Now let's say I wanted to get the second element, this 10. How do I do that? Well, I could say, you know, get at index, right? But then that basically I just have to iterate over it, right? So then I could do something very similar to this iteration with an index pointer. And I say, okay, you know, if index equals, want index, want index, return current.value. Because this is the only way I can do it. I can't access these locations by referencing them directly because I don't know where they are. They could be anywhere in memory. And so what I have to do for here is I have to actually just loop over from the head to the tail and say, okay, stop me when you get to index 5 because that's the only way I have of looking it up. Now, technically, I could have a hash map in here that's also keeping all my indexes, but keeping that up to date would be really complicated. So now let's see, log list.get. Let's say if I get at index 1, and now you can see it gives me that 10. All right, but this is an O of n operation. This is expensive. So then that's the important thing to be aware of a linked list. These here, all these push operations, these are constant time operations because we're not looping when we do a push. We never loop. All we're doing is we're just running over a bunch of variables, a bunch of things that we're doing here. And these are all constant time statements, so it becomes a constant time operation. Iterate is an O of n operation because we're looping over every single element in the array. And you can see we're basically doing that with that while loop. While current is not null, we loop over. And you can notice I use the same pattern here. This is, again, a very common pattern with data structures that are set up this way. Pop is also an O of n operation because of how we've set it up. In a singly linked list where you're popping from tail, pop is an O of n operation because you have to get to the end of the list and then go backwards. Yeah, except it's kind of difficult. So like I have the tail, but then I also have to get the thing before the tail, and to do that is basically a get, which has to go all the way back through the list again. Sometimes what people do is they will pop from the head. There's a special type of one of a queue where you pop from the head and you push from the tail. That can be a singly linked list, and that pops an O of 1. And we'll go over how that works in a little bit. So then we iterate again. This get, though, this is also an O of n. So if I've got an iterate here and then I'm getting inside that, well, then that's an O of n squared operation. So linked lists are very powerful in that they can let you dynamically expand the list, but they also do have some limitations, that being they're kind of, excuse me, kind of expensive to work with. Does anyone have any questions? I'll wait a little bit. And I'll drink some water. I actually have water this time, I learned. All right. So important to note, this sort of thing, I assume there's going to be a thing called linked list. Does everything for you. Well, in JavaScript, no, because the thing is JavaScript arrays are technically linked lists. They already do this, right? If you look at Java, there is actually a class called linked list. If you look at C++, there is actually a class. It's a vector, but it's basically a linked list. Languages that don't have this built in do have classes that do it for you. But in JavaScript, they just have the array, and the array already does a lot of this. Like the array does have push and pop, etc. The other thing that you can do, you have push and pop. There's also shift and unshift. Whereas push and pop, they push and pop from the tail, from the end of the array, right? Shift and unshift, push from the head, push and pop from the head. So just to kind of show you how that would work, they call it shift because you're like shifting an element onto the array. This stays the same because, again, if you have no head, then you need to deal with this. This, however, instead of this.tail.next, this.head.previous becomes new node. And then new node.next equals this.head. And then this.head equals new node. So it's kind of the opposite. And this will actually advance from the head. It'll push the head back 1. So let me see if I can show you what's happening there. So let's say we've got our head node here, right? Basically what we do is we create a new node, okay? That is this right here. So line 40 is this one. Then we say this.head.previous equals new node. And what that does, oh, now I've lost my line tool. There we go. That says, okay, head, you point to here. Right, so that sets up that direction. Then it says, okay, new node.next equals head. That sets up this connection here. And that says this.head equals new node, and that advances our head pointer, because otherwise we're still pointing at this area over here. So that's basically what that code is doing. and it just kind of pushes a new thing on the stack. Now you can see why this is valuable, right? Because now, again, that head could have been here. Now, if I push a new node onto the head, that might be down here. So then all of a sudden my list starts at 1008 and then jumps to 1000 and then goes to 2002 and then goes to 1004. So that is something that the linked list is capable of doing. Now, it is valuable to understand why this is working the way it is, because it'll give you a better understanding of why lists behave this way. You are almost never going to need to implement your own linked list. It is very uncommon. In fact, the way I've done it here is somewhat optimized, but it's not the best way. Because most modern languages have this functionality already built into them. And so, like, let's say, let me just shift here. Shift 200. So then you can see 200 is at the beginning. And so that's kind of, yeah. And even if you get to like Java or C++ or other languages like that, like Objective-C, things like that, they have their own classes that provide linked lists. Even though their arrays are a little different, they have that functionality already built in. The reason I'm showing you this is because, one, you may actually run into an interviewer who hates you and just says, I need you to recreate a linked list class without using any native data structures. Here's how you do it. But the most important thing is I can tell you, oh, this is an O of 1 operation. This is O of 1. This is O of 1. This is O of n. This is O of n. You're just going to be like, okay, but why? This is why. This is an O of 1 operation because it can be done without iterating through the list, because we have access to this tail and head. Pop, same thing. If we have that doubly linked list, we know, and we could do this as an O of 1 operation. Iterate, you can see we are literally looping over the array or the linked list. So of course it's going to be O of n. Same thing with get. We don't have any other way of getting this index. We just don't know. So we have to loop over, and so that's why it's set up that way. Now again, when you do with this in JavaScript, the JavaScript array can index on O of 1. And you notice I keep saying O of 1, O of n, blah, blah, blah. These are things that you need to be thinking about on a, just like instinctively. You need to be thinking, oh yeah, okay. How does O of n work? How does O of 1 work? What is this n squared? Because these are things that people are going to be asking you in interviews. They're going to be asking you, what is the runtime? What is the time complexity of this algorithm? And this is how you figure it out. You need to know these things instinctively because you need to be able to look at your own algorithm and see what it's using. So for example, if I had an algorithm that didn't iterate and that didn't iterate inside that, well, that's O of n squared. If I have to do a get, that's O of n because of how it's set up. This particular one. All right, so let's move on from linked list. And let's talk about, well, let's talk about a couple of the permutations of linked lists, okay? So let's look at a stack, okay? A linked list that can add to the end of the list, but can also only remove from the end of the list. This is known as first in, last out. If you think about this, think about a stack of plates. You put a plate on top, you take a plate off the top. You put a plate on top, you take 3 plates off the top. You put 5 plates on top. You're not taking plates from the bottom of the stack because the stack's going to fall over. Unless you're being very careful, you're not taking plates from the middle of the stack either. You're taking them from the top. And what are stacks good for? Yeah, you learned this last night. This is a linked list. It behaves the same way. The implementation is very similar, except there's no shift and unshift. It's just push and pop. That's a stack. Push and pop both manipulate the tail. So a stack does have to be doubly linked because it needs to go backwards. Up, backwards, right? So let's take a look. Here's a very simple stack. Notice I'm not doing, priority queue is a little different. And we will get to priority queue. So a stack, this one has 4, 5, and 6. You notice it's starting at the bottom. I push 4 in first. I put 5 on top of it. I put 6 on top of that. If I add 10, that goes on top of the 6. I can't access 6, 5, and 4 at this point. They are locked. until I pop the 10 off. Then I can pop the 6. Oops. Okay, so now this frees this up. Stacks are often used when you have a certain number of items that need to be done in the reverse order. So let's say if you've done recursion, right? You remember recursion, where like basically we have let me just comment all this out. If I have a function foo and I have I, and if I is greater than 0, then foo I minus minus, right? And I say foo of 6. Oops. This is a recursive function. Last in, last out. That's a better way of talking about it. I don't remember exactly how I put it in, but yeah. Last in, last out is a stack. No, it's last in, first out. Sorry. Last in, last out is the same as first in, first out. So we don't really say last in, last out. But yeah, last in, first out. That's a stack. So let's say I iterate over this, right? I hit line 95. I go to line 90. And then I hit line 91. The browser is the JavaScript system is using a stack to handle this. Why is it using a stack? Well, because it doesn't want to finish that first function call until it's finished the next one. So our stack is foo of 6, and then it adds in foo of 5, and then it adds in foo of 4, and then it adds in foo of 3, 2, and then 1, and then it actually does hit 0. And at that point, it starts to unwind. It hits line 92. It pops this off the stack. It says, okay, we're done with that one. Let's go back to the next one, because JavaScript needs to remember where it came from. If you call a bunch of functions and that calls a function, that calls a function, that calls a function, it needs to remember that path that you took so it can unwind it as you return. And this is how it does it. It uses a stack. We call this the function call stack, or the call stack. And you may have noticed if you get errors in JavaScript, it will say here is the trace or here's the call stack. And that is actually just printing out this stack. It's saying here's how you got to that error. And here's the variables you used. So stacks are useful for that purpose. They wouldn't want a queue. They wouldn't want a linked list because they don't care about being able to do that stuff. Now, if you're actually doing a standard stack, there are more optimizations you can make, because you can make the assumption that you're never going to be accessing elements except from the top. So in fact, how I would do a stack, if I was doing a stack, is I wouldn't even have a tail. I just have a head. And then I just push, and then I just push to the head. Head.next. Don't even need the previous, right? And then you just push to the head, and then when you're popping, you could say, okay, the value is in the head, and then we're going to set our head to our head.next, except it probably would just be previous, and return value. And so you can notice now, we don't have shift at that point. That's very efficient. We can push, we can pop. We're only dealing with the head. We don't have a tail because we're pushing and popping from the same area. So we just need that one head. The centipede grows and shrinks from one point. So this would be the stack. So if you have a stack, we can, because we're making that assumption that we're only doing it from one end, it allowed us to be more efficient. The other thing with a stack, we don't iterate, we don't have these things. These are not things that need to exist on a stack because, well, maybe you want to have them, but they don't need to be efficient because the stack is not designed to be iterated through. The stack is not designed for you to get something in the middle. That's hard. The stack is designed for you to get something from the top. The only time you're going to get something in the middle or like you're iterating is maybe when you're debugging something. And so we can make those assumptions and make it a little more efficient. Any questions on the stack? And actually, let's see if I take off this shift here. Uh-oh, linked list, stack. Oh, and now it doesn't like so. Oh, because Yeah. I think. What did I screw up here? I screwed up something. Push. It pushes into here. Next. It should be able to iterate over that. Undefined. I don't know. Something about the code got a little screwed up. But yeah, I'm not going to worry about it too much right now. This is the pain of live coding this stuff. Anyway, yeah, this is a last in, first out. What that means is the last element that you put in is going to be the first element you take out. And you can see it's basically a linked list. It looks like a linked list. It just has some kind of assumptions that make it a little bit more lean. But it also means you can't do some things. Any questions on the stack? I do kind of see why this isn't working, actually. Because I get undefined. It should. Oh, yeah, because hi there. That is the first thing, but it should give me the 10 after that. Log. I'll debug this real quick. What is this doing? Oh, it just goes to null. Let's see. No. Oh, you know why? That's why I did this backwards, actually. New node. So what I've done here is I've actually done something like this. We've got our head, right? And I say, okay, add a new element. It says, sure, let me add a new element. And let me point that element here. And here's now our head. But you can see the problem there. The head has no way to go backwards. I've done the arrow in the wrong direction. So what I need to do here is actually have to say new node.next equals this dot head, and that'll reverse that arrow. And I think that should actually work. And this is, when I was in school, we had to build these. There we go. Hi there, 10, blah, blah, blah. Yeah, so it'll still work. In school, we had to build these from scratch in C++ or Java, and we ran into these issues a lot where we just had stuff that did not work the way it should work. Anyway, let's move on. So that's the stack. Let's look at a queue. Queues are first in, first out. Queues are linked lists that push from the end of the list. They push into the tail, and they remove from the front. Okay? Now, you think about the best example of a queue is waiting in line. In fact, if you're British, you would call that queuing. So let's say you're in line to go get movie tickets. Well, the first person that joined the line, they're going to be at the front of the line, which means they're going to be the first person to leave. The last person, as you said, last in, last out, the last person to leave the line or to join the line is going to be the last person to leave because they're going to be the last person that gets their ticket and goes in. Queues are pretty cool. So we have 4, 5, and 6, right? If I add 10 gets pushed in here. And then if I pop, I'm going to pop 4. Though we don't call it push and pop for a queue. We call it NQ and DQ. That's the example I have. So queues are very useful in a lot of cases where if you have things that you want them to get processed in order, then you just throw them on the queue and then you pop from the front of the queue and you handle them. One of my favorite examples of this is if you're implementing like something to recursively look over and check a bunch of objects, but sometimes those objects may have other objects that need to be checked. I would use a queue for that because I would just, the new objects that need to be checked, I'd throw them on the end of that queue. I know they'll get processed eventually, but I want to process the other ones first. So a queue can also be a linked list, except now at this point, we still do need, let's bring queue. We do need the head and the tail. We still need that tail back because we pushed from the tail, but we popped from the head. So this dot tail, oops. Tail equals new node. So we just bring back tail. And then we don't need the previous. We need a single linked list for a queue. Okay. So let's say new node dot next. No, let's say tail dot next equals new node. And then this dot tail equals new node. Now when we're popping, we're still popping from the head. Okay, and that's why we can do it as a singly linked list. The reason is, let's say we have You know what? I need new data here. Okay, so let's see, we have our element, right? This is the head. Okay. Then we add another element. All right. This is going to be, we say, okay, you know, we add from here. It points this direction. We add another element here. Okay. That's fine. We can still iterate over this even because of the way it goes. Now when we're popping, we're removing this one. And this one knows what comes next. It doesn't need to go backwards like we did with the doubly linked list. This one just says, oh yeah, this is going to be my new head. And then, yeah, that's pretty much it. I'm just gonna erase this now. This is gone. This node just disappears. And that's how the queue works. So you can see, again, fairly simple. It's a lot simpler than the doubly linked list. Right? We're just saying, oh, okay, we do have a head and a tail. We push to the tail, which is an easy operation. It's not confusing because we don't have those two things, and we pop from the head. So now, if I run this, oops, stack is not defined because I renamed it to queue. Let me do this. Iteration 1, and then I'm going to put this here. Iteration 2. And then get, just so that it's a little less confusing what we're doing. All right, so iteration 1 has that 5, that 10, that high there. Okay, now iteration 2 got rid of the 5 because our pop now, our DQ, removes from the front of the list. So why are we going all over all these things? Stack and queue and linked list, etc. Well, the reason is they're used for different problems. If you need a stack and you're using a queue, it's not going to work because they behave very differently. If you are using a linked list and you need a stack, you can sometimes get away with it, but sometimes you don't need to, right? And that, again, isn't super important in JavaScript because a doubly linked list can behave as a stack or a queue because it can push and pop from either direction. You can treat it as a queue, you can treat it as a stack. The important thing about that, though, is you have to remember that's what you're doing. If you have something you say, I am treating this as a queue, and I'm running through my algorithm and treating it as a queue, and suddenly you start treating it like a stack, your algorithm probably is not going to work. Because that data, you had an assumption about that data, and suddenly you're doing something that breaks that assumption. Assumptions are extremely valuable in algorithms because it lets us write code where we don't have to do checks. So if I'm assuming that I have a list that I'm treating as a stack, then I can make the assumption that if I pop from that stack, I'm going to get the most recently added thing, right? First in, first out. Or no, sorry, last in, first out. That's an important assumption that I might be making in my algorithm. With a queue, on the other hand, I'm assuming that when I pop, the first thing that I put in that queue is going to get popped. All right? So it is really important to understand this stuff and to understand how it works. The important thing about queue, though, push and pop, they're still O of 1. Iterate is still O of n. Even though we've changed kind of what it does and how it works, it hasn't changed the time complexity. So you don't need to remember a time complexity for a stack or a queue. You just remember the time complexity for a linked list. Any questions? Oops, that's not where I want that. All right, so let us move on to the next one. Priority queue, which was already mentioned in the chat. A priority queue is similar to a queue, but has a priority that can move it up and down in the queue. So the first element you pop is not always the first one you inserted. It is rather the element with the highest priority. This is often used for message queues because the longer, let's say you have a message that you need to send, you may say, yeah, this can get delivered in the next half hour. It's not that big of a deal. Okay, well, the system probably isn't going to deliver it at first because it's got other messages it needs to deliver. However, as we get closer and closer to that half-hour mark, it becomes more and more important that that message get delivered. So the system will start to say, oh, you're more important. We're going to bump you up the queue a little bit more. So that's how a priority queue works. And it's very similar to a queue in a couple ways, right? So we have a value and a priority associated with those values. Priority could be a number, it could be a string, it could be, as long as you have some way of determining the ordering based on the priority, you can do it, as long as it's easily figure outable. So 4, 5, and 6 with a priority of 30, 5, and 15. Now you notice already these are out of order. 4 is first because 4 has that priority of 30. In a normal list or queue, 5 would be next. But instead 6 is next because 6 has a higher priority, and then 5. Kind of think about like if you go to an amusement park and there's like VIP ticket holders that they can jump the line. All right, that's kind of what a priority queue does. So let's say we insert 10 with a priority of 20. Well, you see that doesn't go to the end of that queue. That goes in between 6 and 4 because its priority is in between there. It gets shunted in to that system, right? Queue contain 4, 5, and then, yeah, so we add that. Then when we pop, we would, like normal, if we dequeue, we're going to dequeue 4 first, but then we're going to dequeue 10 afterwards. Unless someone else comes up and says, you know, oh, I have something that's a higher priority than 20. Priority queues, kind of useful, especially if you're doing with them with algorithms. The issue with priority queues, though, is they're a little expensive to insert data into. Now, if you're doing them as a linked list, let's look at the priority queue here. Priority, our node now has to have a priority, okay? And so now when we're doing a push, we need to actually tell it what the priority is. Okay? Now the issue is we can't just push to the head or the tail. That ain't going to work. We actually have to find where in the queue this priority works, and that means we have to iterate. So what we're going to do is we're going to iterate, and we're going to say, okay, if current.priority is less than our new priority, well, then we know we got to add it onto the end of this one. Now, inserting a node in the middle of a thing is a little complicated. So let's do this. Let's get a new. So let's say we've got 3 nodes, okay? And we've got some arrows between them, right? And we do. This doesn't have to be doubly linked, and so I'm going to see if I can do a priority queue without doubly linking it. But let's see. So if we want to insert a new node, like let's say we want to put this node in here, the first thing we have to do is we have to tell this node, okay, we have to set up 2 relationships. We have to set up this relationship, right? And then we have to set up this relationship. And then we have to get rid of this relationship. And now that node has been inserted into that chain. So that's how we insert a new node in between 2 things. Okay, so let's say we get to here, while current is null, if we find a place where our priority is less than the priority we're trying to insert, we know that our node needs to go after this node. Okay, that's just, it might not entirely be that easy, but we assume this is in order. Okay, priority is less than this. Then we say, okay, now we have to kind of insert it in. So, all right, so our current, if our current dot, well, first of all, let's take our current dot, what do we have? Next, right? Because this is a doubly linked. See, this is where things start getting complicated. Because I have my current, and I have my current dot next, and I want this next to start pointing at the new node. Except it doesn't point anywhere because it doesn't have a previous. So, new node dot next equals current dot next. And then, I say current.next equals new node. I guess that's not as that complicated because it's only a singly linked array. All right, and then we're just going to return at that point. We're going to break out of this loop completely and this function because we've inserted it. If we get down here, it means that our end node is the highest priority, so we're just going to push it onto the tail. Okay, this dot tail, oops, new node dot next, this dot tail, and then this dot tail equals new node dot next. So what that's basically doing is we're saying, okay, let's say if we started at the head, we got to the head and we find out, well, we need to push this in front of the head. Well, almost immediately we would be pushing it in at the current. I don't know if this code is going to work. I'm going to have to test it. Let's see. So whatever point we get to in our system, and I guess let me actually redo this because we're using a singly linked list. Okay. So we have our nodes here. I have a singly linked list going here. And then we have here and here. So let's say we need to insert to the head, right? Well, that's pretty easy. We just put that and then we set this and then we set our head pointer. Except we're not doing that. So I need to say if that current.next equals this dot head equals new node. What that is doing is that's just saying, hey, if our current pointer that we're on is the head, then advance the head along because that's important too. Oops. Then if we need to insert it in here, we just say, okay, let's pop that in here. And then we're going to point this one up here. Okay. And then we're going to erase this link. And we're going to create a new link there. All right. So that's how we insert stuff into the middle of the node. We're doing that now based on priority. Okay. So let me actually pop the priority in here as well. And then priority. So let's push this in here with a priority of 10. This one is a priority of 5, and this one is a priority of 15. So it should go right to the front, right? And let's just run this and see what we get. We get an queue is not defined because it's a priority queue, of course. Oh, undefined is not iteratable. My list is not iteratable. Structure cannot define read property symbol iterator. Oh, because I put this in. Yeah, my bad. Sometimes JavaScript gives you very confusing things. All right, 5 undefined. Oh, because I never actually set the priority. This needs to be priority. And there you can see how that is undefined down there. There we go. So now, our first iteration, we start off with 10. We start off with this. Oh, and you notice this never gets inserted. So there's a problem there. If our priority is always lower, we should be getting down here, right? Current low, yeah, we should get to this point. No, you know what? This is backwards. It should actually be this dot tail dot next equals new node. That's the problem that I'm running into. I did the arrow backwards again. You can see how that gets very easy to do. There we go. Okay, now we have this, this, and this. These are still completely out of order. This high there should be above that. Let's see. Next equals head. Next equals that. Current. Oh, this should not be there. That next should not be that. But I'm not advancing the head for some reason. Yeah, so this never happens. Right, because it needs to be against current, not current.next. There we go. All right. So now, oh, and now it just completely eliminated itself. This needs to be current. There we go. Now we finally have the working algorithm. You can see like there's a lot of little things you got to tweak on this. The priority queue is complicated. But now I've inserted this, and then this high there gets pushed to the front because it has a higher priority. And now when I pop, it pops that one, etc. Priority queue. The problem is now push is an O of n operation because I may have to loop over the entire list. Generally, what real priority queues do is they should be implemented using a binary tree approach, where they're just set up in the right way so that it's a balanced tree where the highest priority is at the top. And that means that inserting a new node can be done in O log n. So this is an inefficient way to do a priority queue. I just don't want to take 45 minutes to do a binary tree because binary trees are kind of complicated. So yeah, that's kind of what you have there for priority queue. I've done it in a slightly inefficient way. If you are using a true priority queue class that's like part of your like a library or something, then you'd probably be able to get it done in O log of n, but this is an O of n insert. The reason that's important to note is because that's kind of expensive. That is kind of expensive. So the priority and having that be able to pop that priority appropriately, you kind of want to think to yourself, is that really important? How crucial is it that I really need that ability? Because it might be expensive to give me a data structure that has that ability. If you add the assumption that all of your items are going to be in priority order, then you also have to have the assumption that it's going to be a little more expensive. So yeah, priority queue. Any questions on that? I'll wait a couple minutes because I'm sure people are talking. Or not talking, typing. If they are typing, I'll give people the ability to type. Yeah. I think a lot of, you could do a priority queue using a hash map as well, where you just have the hash of the priority and then finding the highest one. Well, no, because then you still have to know which is the highest one. So, yeah. Anyway. I did that. I was not efficient. Yeah. No. No, I would believe that. Because you still kind of have to loop over the whole thing to figure out where the highest one is. Yeah, data structures, some of them, like, you think they're a magic bullet, and they're just not. All right. So let's take a look at hash map. Hash map contains a mapping between keys and values. It uses a hash or algorithm to determine where in memory the key comes. So this is actually kind of similar to how an array operates, except much more complicated because hash maps can also grow dramatically. Indexed by any type of data that can be hashed. So you can have string keys, you can have integer keys. If you have an object that can turn into an appropriate hash, you can do an object, can contain any type of data. So let's take a look at the hash map. We have a hash map with key ABC, which goes to data value of 6. And imagine these are all the addresses I have for my hash map. I have 10 different addresses. This, what I'm about to show you here, is a very poor implementation of a hash map algorithm. The version that you'll use in like the JavaScript object is a lot better. So first thing I'm going to do is I'm going to take the ASCII versions. So I'm turning this string into a number, right? And I'm adding all those numbers up. 294, because these are the 3 characters. Then I'm actually going to take the modulus of 10, and that comes out as 4, so that's where that is. What is the value of this? Well, if I need to look up the hash map, the value at key ABC, I just repeat this algorithm, and I know immediately which memory address that value is started in. That's the value of the hash map. I can look it up very rapidly. So if I want to add another one, high goes to 200, same thing. I take the 2 keys here, modulus it by 10, I get 9. These are completely in different places now. And a good hash map algorithm probably has something much smarter to conserve memory in better ways and just deal with it in more appropriate ways in handling these keys, but this is basically the idea behind a hash map. The key gets turned into, by some algorithm, the memory location that the data is at. Now here's the fun part. A JavaScript array is technically a hash map. The reason is it's not a linked list. It's not a standard array because you can add elements onto it. You can append new elements. You can push pop. You can shift unshift. Those are all things that actually exist as functions on the JavaScript array. But you can also index it. And that is something a hash map can do. A hash map indexes by a single key and can in constant time look up that value. Linked list cannot do that. So JavaScript arrays are actually hash maps. Have I blown your mind yet? There is also the actual object in JavaScript, which is also a hash map, but that uses non-integer keys, whereas the array uses integer-based keys because it can look this stuff up, right? So it's not like a true, it's kind of more an amalgamation between a hash map and a linked list, because it's a linked list that knows its own size and also knows how to look up the specific location in memory where the data is, but it can also expand. So it probably looks extremely weird under the hood, but it definitely, the JavaScript list behaves more like a hash map than it does behave like a linked list. So, you know, just some food for thought. Do I have? Nope. So a hash map, I'm not going to try to do a hash map implementation in code because one, JavaScript already has a perfectly good hash map implementation. It's just the object. The important thing to note about hash maps is that their insert, deletion, like push and pop basically, are always O of 1. They're always constant time because if you have a key, you can always look up that value immediately because you have this formula which doesn't rely on how many elements there are in the hash map. So hash maps are very powerful for doing data lookup. If you need to do some lookup, a bunch of lookups on something, and you need to look behind and like figure out a certain computed data, for instance, which is what I use hash maps a lot for, you build a hash map. It is O of n to turn a list into a hash map. Just keep that in mind. So if you have a linked list or an array and you turn it into a hash map, you have to iterate over the whole array to do that. So it does get a little expensive. However, it also means that once you have that hash map, any other lookup is constant time. So if you know what you're looking up and you can build your hash map appropriately with the appropriate keys, that does make it very very easy. And I think I did this in one of the leetcode videos where I used a hash map, or at least I talked about it. I don't know if I actually got around to it. So yeah, hash maps are very powerful. They're part of a larger class called map, but in my time, I have never seen any other map than a hash map really be used. You know, like I'm sure there are others, but they're really not that common, and I don't think anyone would expect you to know this. But hash maps are your friend. However, the important thing about hash maps is you have to remember you have to put the data into the hash map. It's very, very rare that you get an algorithm question where they've already built a hash map for you. And building the hash map can be expensive. Utilizing it once you built it is fine, but it itself can be expensive. Anyway, let's move on. Well, actually, I guess, are there any questions on hash maps? All right. So let's talk about trees. Trees are a very weird data structure. Trees are also a very popular data structure because they're very efficient if they're set up properly. Trees are a branching structure that flows from top to bottom. Like the top is the root, and then you've got a tree structure. So it's kind of, if you flipped it the other way around, it would look like a flowering tree with its branches. Oh, excuse me. We can go over heaps because heaps are actually a type of tree. So yeah, we can talk about heaps. Um, I did look it up after I made this presentation because you mentioned it in the server, and they're basically a tree, or they're actually a form of binary tree, from what I was reading, which we will be going over. Each node in the tree has between 0 and infinite children. Those nodes can have their own children. So trees are kind of like a list that started sprouting stuff off to the side. There's a top level node that has no parent. It can have children. That is the root of the tree. That is the node that we keep track of. We don't generally keep track of all the child nodes. We keep track of that root. Trees can be sorted or they can be unsorted. Unsorted trees are a lot easier to insert into in some cases, but they also, you can't make assumptions about them, so they're honestly not as useful. Very few algorithms I've seen make use of unsorted trees. They're usually sorted, and we'll get into what that means. Trees can also hold any kind of data. So let's see. Binary tree. So this is the most common form of tree that I've ever seen anyone run into. This form of tree allows a maximum of 2 children per node. When sorted, this property allows us to quickly search through data. I have a video up on various searching algorithms, which goes over binary search, which if you look at that, you can see a good example of a tree. Let me see if I actually did one here. I did not. Okay, so let me show you what a binary tree kind of looks like. Okay. Binary tree starts off, I have to make this, oops, a little bit taller here. Binary tree starts off with a root node. This node does have a value, right? And what we start off with is say, okay, we got a root node. When we insert a new node into a tree, our binary tree, we have to determine, are we inserting it to the right or to the left? And in a sorted binary tree, that whether we go right or left determines on whether or not the value we're inserting is bigger or smaller than the value already at the node. If it is smaller, it goes to the right. If it is bigger, it goes to the left. So let's say we had, let's say we had 4 here, okay? And then we want to insert 8. Well, 8 goes to the left. This is not left. This is right. 8 goes to the right because it is bigger. Okay, 8 goes there. Okay, now let's say we want to insert 6. Well, now we say, okay, well, 6 is bigger than 4. So we go down here. We go to the right. Then in 8, we get 8, and we say, okay, well, 6 is smaller than 8. So that goes to the left. Put 6 here. Okay, now let's say we want to insert 2. Well, 2 is less than 4. So we're going to go here, and we're going to put 2. No, that's not the text. And if we did 3, 3 would be to the right of 2. So you can see kind of how this branching structure slowly gets formed, and it could look different depending on how you insert your data node. So like if I was going to insert 3, this is going to get a little crowded, but basically, oops, that would end up right here. And so in this case, you probably want to put your nodes a little bit further apart. So now if I'm looking for 3, I know it's less than 4, and I know it's greater than 2. So this lets you very quickly follow a path down. Binary trees are very good for search. The most efficient search algorithms are binary searches. And that's because you don't have to loop over the entire array. Again, I covered this in the search video. Binary trees are also really cool because they just have there's multiple ways of searching them. There's multiple ways of adding. There's ways to balance a binary tree. Inserting into a binary tree is going to be a log n operation if it is sorted. It is going to be a little complicated. Searching a binary tree, on the other hand, if we want to look for a certain value in an array or a linked list, that's O of n. No ifs, buts, and ands about it. It's an O of n. If we want to search for a certain value in a binary tree, it is going to be an O log n operation. That's just how it works. Binary trees are O log n. And there's ways. There was actually something I watched the other day about a Fibonacci heap, which was one of the most complicated data structures I had ever seen. And I'm not going to cover it today because I didn't fully understand it, but it was basically like constant time for everything except for like one particular thing. And it involved a bunch of different binary trees. Very confusing. Anyway, binary tree, this is how it works. This is how it operates. So let's try to create one. No, I'm actually going to comment this out too. Okay, class, we still have a node. Okay. Nodes are important. Constructor, value. But the thing that we're going to do here is we actually have this dot value equals value, and then we have children. We have the left child and the right child. If we were dealing with a standard tree, we would just have a list of children. We just have an array of children because a standard tree, the nodes can have more than 2 children. But this is a binary tree, so we're just going to do left and right. Class, binary tree. Okay, so the constructor, we do something very similar. We say root, right? So we start off with root. Now, if I'm going to insert data, value. The first thing, this is going to be very similar. If I have no root, then I'm basically say, okay, this dot root equals, well, let me make a new node first. Node value. This dot root equals new node. Again, this is setting the root if nothing exists. Otherwise, it gets a little more complicated because we actually have to iterate again. However, the way we iterate is going to become important, okay? So let's say, okay, we're going to do a current equals this dot root while current not equal to null. And I'm going to look at this and say, okay, if value is less than current dot value, then we're going to iterate to the left. We're going to say current equals current dot left. And actually, we want to do something a little bit more complicated here. But otherwise, if the value is greater than, oops, basically else, the thing is about a binary tree is it doesn't always handle having the same value inserted into it twice. How would you do that, right? Like, so if we look back here, let's say I wanted to insert 2. Where does 2 go? The other thing is 2 is already in the tree. So basically, if we find the value already in the tree, it's kind of depends on what your algorithm's doing. But in this case, I'm just gonna say give up. Right? I'm gonna say we're done. We're already in here. If value so equals, well, let's just do this. Current dot value. If it's greater than it, then current dot right. Okay, and then the final case would be if it's equal, in which case else we just break. We're done. Actually, let's just return. The value already exists in the tree. We don't need to insert it again. Again, for your particular algorithms, you may want to do something different here. So here's the fun part now. If we don't have a current dot left, so if not current dot left, well, current dot left is going to be new node. We're going to put that as the left node. And then we're just going to return. Otherwise, we're going to go to the left. And we're going to check and see that again. So if I'm inserting that 3, right, I say, okay, it's less than 4. Let's go to the left. It's greater than 2. Well, 2 at that point, if I was inserting 3, well, let me insert something that actually isn't in here. Let's say I'm inserting 10. I say 4. Well, I have a right branch to take. So I need to take that branch because I need to go greater. Okay, here now we have this 8. Okay, and we say, okay, I need to go right again, but I don't have a right branch. That means I get to create that new node and link it up. So that's basically what I'm doing here. And so now similar thing for the right. If there is no right, then we just insert the right. Current equals current dot right. return. So now what I'm going to do is let's make a new tree equals new binary tree. Okay. Now the problem you start running into is how do you display this in a console? Is there a circumstance? Not in a binary tree. The question is there a circumstance where it's possible to have 3 or more childs from the same parent? Not in a binary tree. A binary tree specifically can only have 2 children per node. And that allows us to do those left-right searches. A standard non-binary tree can have 3 children in the same parent. But that's just a regular tree. That's not a binary tree. I've never not worked with regular trees that much. Anyway, so let's insert 4, right? We're going to insert 2. We're going to insert 3. And let's insert 8. And then I'm just going to console log tree.root because I want to get that full root out. All right. So now you can see, here's our 4, right? Our left node is 2. It has no left. It has a right of 3. And the right node is 8. I know this isn't the prettiest visualization, but visualizing a binary tree and actually writing the visualization code for that is kind of a pain. Because you have to know how many layers it goes down and how far to move across the nodes. And yeah, it's just not something I want to do right now. So you can see here's our root node. To the left is 2. To the right of that is 3, like it should be. And then to the right of that is 8. Now, if we want to search this, it becomes quite easy. So if I say like console.log tree.find, let's say I want to find 3, right? So let's make that function. Find value. Well, basically, I'm going to do a very similar loop to this. Okay. Oh, I don't want the function. And I'm going to say, okay, you know, if, let's see. Except in this case, we're going to say if we find this, then we're going to return true. And if we don't find it ever, we're going to return false. Okay. Now I look for that, it gives me true. If I try to find something like 30, it gives me false. And what it's doing is when I say find 3, it basically says, okay, great. 3 is less than my current value, the value of my root. So I'm going to go to the left. Current.left. It loops again, says, okay, 3 is greater than my value 2. So I'm going to go to the right. It loops again, and it says, oh, at this point, 3 is equal to my value 3, so I found it, I'm going to return true. For the 30, it says 30 is greater than 4, so I'm going to go right. Okay, it goes into this one. And that says, okay, cool. 8 is, or 30 is greater than 8, so I'm going to go to the right again. And that says, oh, well, current is null, breaks out of the loop, and hits the false. This runs in O log n. Because the maximum amount, remember, big O notation is the maximum amount of times that loop will run. The maximum amount of times this loop is going to run is based on the maximum depth of this. So 1, 2, 3. How long of a path can you trace always going downwards? The maximum is 3. There is, what, 1, 2, 3, 4, 5, 6 elements in here. Okay? I could add one more element, and that'll bring me to 7. As soon as I go up to 8, that maximum depth jumps again. So technically, actually, the maximum depth here is 2. It'll jump to 3 at that point because 8, right? Which is the logarithm. That logarithm grows very slowly as the number of elements grow, and that's what's powerful. Because if I look at like, well, let's see. Where's my calculator? Can I do logarithmic on this calculator? I think I need to put in scientific mode. Scientific. So if I put like 1,000,000, right, and I take the log of that, that's 6. That's not too bad, right? And I think actually this is it has something to do with like log base 10 versus natural log, but it's a lot smaller, and 6 seems like very small for that. But basically, so I think I did that calculation a little wrong. But basically, the longer, oh no, because it's a log base 2, not a log base 10. That's why. It's a log base 2 because it's a binary tree. So it's a little bit bigger than 6. But basically, for every and as you grow, the n of it grows slower because the number of rows, like right now, there's 4 row elements I can fill. The next time that's going to be 8. The next time it's going to be 16. So I can add double more elements into each row, so it's less and less expensive to add more elements the more elements I add. Binary trees are cool like that. All right, so let's talk about heaps. I did actually look up heaps here, heap data structure. This, if you're looking at data structure, Wikipedia is great with data structures. So actually, let's see if I just look up heap data structure. Here we go. You can tell I've been there as well. So heap is a specialized tree-based data structure. What does this tell you? Immediately when you look at tree, it's this kind of format, right? And you can see this tree has 3 children. It is an almost complete tree. I don't know what that means. Yeah, k equals t, each node has most 2 children. Okay, so that's binary, right? Binary tree. This satisfies the heap property in a max heap for any given node. If P is a parent node of C, then the key value of P is greater than or equal to C. So if you look here, I believe this is a max heap. Yeah, binary max heap. So in this case, the highest value is at the top. So when we sorted our binary tree, right, we did our insert. We did our insert basically on trying to get the middle value. And that's why we said, oh, you know, value less than current value, value greater than current dot value, etc. That's because our tree was trying to get the median value to be in the middle. Values on, well, I mean, technically not the median, really, because there's ways to make sure it's the median, and that's actual balancing the binary tree as opposed to sorting it, which is a totally other thing. Balancing trees is an expensive operation. And it involves like a lot of node rotation, and I don't fully remember it off the top of my head. But this one, we're saying, okay, we just want to make sure that everything to the left of this and everything to the right of this has that property. In their particular case, they want the highest value to be here. Now, how would you handle it? Let's say I need to insert like 18 into here, right? So what I would do in that case then, because of the way this max heap is set up, is I would know 18 is less than 100. Okay, it's less than 19, but it's greater than 17. So I have 2 options here. Either, and probably what I should do in that case is I should actually push it onto the right. Well, no, actually I shouldn't. Yeah, maybe I should push it onto the right. Though it looks like this is not, yeah, it looks like this doesn't balance correctly. Let's see. The node top of these called moot node and min node. By a tree, data structure. There's no implied ordering between siblings or cousins, and no implied sequence for an order traversal. The heap relation is only between nodes and their parents. So really, in that case, I could put the 18 on either one of these, right? I could probably push it onto the right or the left. It doesn't matter. The important thing here is that the node is always less than its parent, which means if you're trying to find the smallest child, you just traverse down to the roots, right? And you know the smallest element's going to be here, but the biggest element's always going to be at the top. Why is that useful? Well, maybe you're trying to build a priority queue. And maybe this is how you want to build your priority queue, because the highest element needs to be at the top. This actually looks like a really nice structure for a priority queue, in fact, because the highest priority is always going to be your root node. When you pop that, the next highest priority is going to pop up, right? So you're actually going to have to rotate your keys a little bit when you do that. Not the biggest deal. A min heap, on the other hand, would be the opposite, where the minimum value is at the top. So basically, these are data structures where, like, it depends on what you're looking for, but I could see a lot of cases where I would really, really care about where my smallest or largest element is in the array and be able to pop that and get the next smallest or largest element to kind of automatically flow up or very cheaply flow up. And the heap, max heap or min heaps are capable of doing that. Oh yeah, you can see. One maximally efficient implementation of an abstract data type called priority queue. In fact, priority queues are often referred to as heaps. So there you go. That's what a heap would be good for as a priority queue. I did mine with a linked list. Not the most efficient way. You can see how this would be more efficient because that maximum, the next thing you're popping, is always going to be floating to the top. That does mean that inserting into a priority queue at that point with this data structure becomes O of log n. And popping from the priority queue becomes an O of n. Well, that actually technically is also O log n because when you pop, you have to possibly rearrange these nodes. So that could be a little bit more expensive. Or when intersections need to be dispersed with removals. Let's see, common involve heaps, find max, find min, extract max or extract min, replace. Yeah, and so you can see a lot of these things. How efficient are these? You have to think about what it's actually doing, but because it's on a tree, it's going to involve logs. Heaps usually implemented as array. Child relationship is defined implicitly by elemental index in the array. And this actually is kind of nice because it's an easier data structure to deal with. And if you're trying to figure out where things go, you just move things around. So yeah, that's kind of interesting. Index contains the root node. Next to index contains the root's children. In binary, you have that, right? So there's 8. The next one, you add 16 on and add those all in. Yeah. Bunch of other stuff. There's a bunch of other different kinds of heaps you can have. You can see all the timings here. Very useful stuff. You can see find max. Obviously, find max is easy. Inserts log n. Delete log n. Delete is the same as pop in this case. Oh yeah, Fibonacci heaps. These are fun. You can see Fibonacci heaps. Their delete is O of n. What's this? This is not O. This is like middle O. But their insert, I think what this dash means is like over time. So it's expensive at first, but over time it kind of averages out. But you can see a Fibonacci heap is extremely efficient. It's also extremely fucking weird. Like really weird. Yeah, you can see there's a couple of these that like it depends on what you're trying to do. Like maybe you're trying to do increases. Well, maybe you want a 2-3 heap then. I can tell you, I don't use these very often. You know, if I need to build a priority queue, this seems like a good way to build it. In fact, if I was asked in an interview how to build a priority queue, I'd probably do it in a linked list first and then transition to this because it's just more efficient, but it's also harder to build. So the thing to bear in mind when building your own data structures is that it can take some time. You saw I got the linked list pretty easily. Well, that's because I've practiced building a linked list specifically. Hash map, I wouldn't build a hash map because it's built into most languages. Binary tree. Binary tree is a good thing to know how to build because JavaScript doesn't have a native binary tree. Now you can, and I've done this a couple times, if you have a sorted array, you can treat it like a binary tree. So one of the leetcode videos that I've done does that. And so that can be kind of efficient. But yeah. Let's see if there's any other data structures. Let's see if I just get a list of data structures. Let's see if there's anything else. Oh, you can see here's the here's a hash table. So you can see their hash function, put stuff in various places. Dijkstra's shortest path. See, those are fun. Yeah. Dijkstra's shortest path is really fun. That is actually, there's actually a data structure that Dijkstra's is designed to run on called a graph. And so a graph is a tree, except nodes can loop back to their parents, right? And so what that looks like, let me just take this over again, is let's say I've got a node and a node and a node and a node and a node. It's like, you know, this one goes to here, to here, to here. This one might go over here. It might come back here. So this is a graph. All right, and there's ways, there's algorithms that you can do on a graph to find what is the edge of a graph, right? Or like where is paths? What are nodes that are unconnected or only connected by one thing? Graphs are kind of interesting because they can be implemented like trees, except there's not really a root node. You just start off with like you have a starting point and an end point, and how you get there. Yeah. The extra shortest path is an interesting one. I don't know if I've ever actually implemented that myself. The other thing about graphs is that there could be cost to travel these. So let's say like maybe this is the shortest distance, but this is a cost of like 40, and this is a cost of 5, and this is a cost of 15. Well, this is the cheaper path, right? Between this node, this node, this node, you don't want to take this path. So how do you calculate and figure out what those cheaper paths are? Let me see if I can actually show you. I have one of the really common things for this is where's my A star? Do I not have it anymore? Nope. I thought I had. I have a specific thing that does A star, which is a common pathing algorithm. I just don't know where it is. So I'll have to see if I can find that because A star is a really, really interesting algorithm. It does something similar, but it's more meant to a rectangular grid rather than points. So yeah, this is a graph. You may run into graphs occasionally, and the graph is just basically all the nodes are connected to different nodes, and they have some cost associated between getting between those nodes. This particularly is a really good way of showing servers on the internet or like routers. So if your computer is trying to figure out how to talk to some other computer, it will actually use tables, routing tables, to figure out the quickest path to get there, because that's kind of what you want for a router, right? And stuff like Dijkstra's is actually similar to what we use. It may actually be what we use. It's been a while since I've done any of that work, but algorithm and graph paths like this with cost is how we determine the best paths between data, and that data gets updated a lot. There was an interesting incident once where some router started lying. I don't think it was malicious lying, but it wasn't telling the truth about how cheap it was to get stuff there. It said like, oh, it takes a millisecond for me to talk to all these other routers, when in fact that wasn't true. It was probably someone misconfigured it. But immediately all the internet started sending traffic there because it was like, well, that's way cheaper than whatever my other path was going to be. Go ahead, let's do that. So that led to some interesting updates to those algorithms. Most algorithms are not built around security. Most algorithms kind of assume that the data they're being put into them is true. I have yet to write an algorithm where the data, like, we couldn't assume it was accurate, because that kind of defeats the purpose of the algorithm. But yeah, graphs is the other one that is kind of fun, and there's a lot of stuff around graphs. Let's see what else we have. Oh, list of data structures. That's what I want. Okay, we got primitive types. We know most of these. Arrays. We went over arrays. Records are basically classes. Unions are kind of a more efficient version of classes. Lists. We talked about lists. That's a linked list. Associative array is a hash map. That's a multi-map. Generalization, much more in value. Oh. That's kind of interesting. So multi-map would basically looks like it's an object where the key is, or the value is an array of multiple objects. Tuples. Tuples are kind of interesting. Okay. JavaScript itself does not have really a native tuple thing built in. But a tuple is kind of like, it's like a pair, but it's an n pair. So it could be 3 different objects, right? And so some languages define those strictly. Like if you have a tuple that's a string integer string, then you can't put any other data types into there. It's what I've most commonly seen tuples used for is if you need to return multiple values from a function. So in JavaScript, we probably just use an array, right? Or like an object. But in Python, for instance, you could use a tuple, and it returns multiple objects. And it's kind of like, it kind of behaves like an array, except it has some weird restrictions on it. If you're working in JavaScript, you're probably not going to run into tuples that much. But they're still kind of useful to know about. Sets are very interesting. Sets are similar. I probably should have covered sets. JavaScript does have a set. If you want to do a set, you'd say const foo equals new set. And that's just a built-in thing. What sets do is they are similar to lists in that they contain data, but they contain unique data. So if I say foo.insert 5, foo.insert 10, foo.insert 5, and then console log foo. Oops, I think it's add, not insert. Right. You can see it only has 5 once, even though I added it twice. So sets are deduplication systems. They will not insert an element if they already have that element. And that can be useful for a lot of reasons. Like maybe you've got a list of years that you just grabbed off of like a map function and you want to deduplicate them. You can just throw them all into a set. You can create sets from arrays as well. So sets are really nice. They are unordered. So they don't, or not that they're unordered, but they don't preserve any kind of real order. If I was to loop over this, I get 5, I get 10, but there's no real necessary guarantee, I think, that that order is actually going to preserve as you insert more items into the set. I don't actually know. I would imagine that sets probably behave a little bit like hash maps under the hood, where they are taking their value and they are hashing it so that they know whether or not that value, they've already seen it. So yeah, sets are kind of interesting. They can be really useful if you've got a large data set that has duplication and you just want to dedupe it. You just put it into a set. It will run in O of n because it has to run over all the elements, but after that it's deduped. That can sometimes be kind of nice if you're just deduping as part of an other algorithm. So yeah, that I would say sets are not used like amazingly often, but they're still good to know about. Let's see what else we got. Multi-set is kind of the same thing. I think a stack we went over, queues we went over, priority queues. Double-ended queue is basically a doubly linked list where you can add and remove from both sides. This is how JavaScript arrays generally behave. And then we talked about graphs, right? Trees are actually a type of graph. They're a unidirectional graph. Heaps also, but graphs also can be, like you can see in that example here, they have vertices that there's no defined head, right, or root. You just add stuff in. Let's see what else we got. This is definitely a useful one to look at. For most of these, what is a container? Okay, that's not something we really need to care about. Lists, maps, sets, queues, stacks, priority queues, double-ended queues, graphs, trees, heaps, binary trees. Know what these are. Like you can see, some of these I don't really know. Like I've not really ever used a multi-set, right? Like I'm not completely sure what that even is. No, just know their names and know how efficient they are at what they do. Knowing why, so I've been over for a lot of these why they are the efficiency that they are. It's not the end of the world if you don't completely understand that, because a junior engineer is probably not going to be asked that. Like, I'm probably not going to ask a junior engineer why is a hash map so efficient. And of course, the answer to that is it uses a hashing algorithm to map a key directly into a memory address so that it knows how to look it up very quickly. I wouldn't expect you to remember that. What I would expect you to remember is that it does, if you're doing a set or get on a map, it's an O of n operation, and how you would use that in an algorithm. That is more important. So keep that stuff in mind. A lot of these things are valuable. Let's see if there's any others to go over. You can see sets are not ordered. The elements have some explicit order. An element can be served before or after another element. Generally, if you're you can loop over a set. And at that point, the set will give you some order. The ordered here basically means that that order is kind of kept with you, right? So if you have a list and that order and you insert another element, that order doesn't necessarily fuck up for the rest of the elements. Whereas in the set, it might, depending on how the set is implemented. And again, this for the set, that the fact that it doesn't have to be ordered, that is an assumption we can make about that data that allows us to write a more efficient algorithm for it. Oh, bitmaps are fun. Bit area bitmap index. Bitmaps are actually there. You may run into them a little bit, but bitmaps and bitmapping is kind of storing binary data in a number. Okay, so let's say I had a number and it was like, let's just say 43. All right. Now let's take a look what that number looks like in binary. I could do this off the top of my head, but I'm not going to. I'm just going to use a converter. So I look up here, I say, okay, what is 43 in binary, right? This is the binary equivalent of this. What that means is that in this number, in like, let's say I'm doing an 8-bit number, I have the ability to store 8 flags, 8 Boolean values. So I could say maybe this is something on like a player character where like, are they alive? Are they currently encumbered? Do they have inventory slots? Are they wounded? Stuff like that. And you can see rather than declaring 8 different variables and storing that data in 8 different memory locations, because if you store a Boolean, depending on the language and the system you're working on, it may actually allocate 32 bits for that Boolean. Just because if the language isn't smart enough and your processor isn't smart enough to compress them together, the smallest amount of data that can be allocated to a single variable in most modern systems is, actually in most modern systems, it might actually be 64 bits at this point, which is not a super big deal if you've got thousands of gigabytes of memory, which many of us do. But if you're trying to save data to a file or like transmit over the internet, it can be useful to bitmask. I'm not going to go too deep into how you get data in and out of a bitmask, but basically that's what it is. It's you take a number, you break it down into its individual bits, and you assign kind of a context to each one of those bits. Yeah, that's basically it. But yeah, bitmaps are kind of fun. Dope vector sounds kind of dope, honestly. A lot of these I'd never heard of. Bitboard, circular buffer control table, image. Well, we know what images are. Straight tree matrix. Matrices, probably don't run into those too much. Usually if I had to deal with a matrix, I'd store it as a nested array. Parallel sector array. Doubly linked lists we went over. Array list. Linked lists we went over. Singly linked lists, right? Self-organizing list. That sounds kind of interesting. You can see there's a lot of these. I can say of this list that I'm seeing right here, I've never even heard of 90% of these. A lot of times, these sorts of things, like the really, really in-depth versions of these, are sometimes used by people designing computer languages or trying to come up with better ways of sorting, for instance. Like, if someone could come up with, right now, the best sorting algorithm we have, I think, is n log n. If someone comes up with a sorting algorithm that's just O of n, that would be huge. Like, that would be just one of the biggest things that's happened in 30 years for computing. Okay, maybe that's a little over the top. But yeah, a lot of these you're never going to worry about. You're not going to worry about these, like whatever a gap buffer is. If you do know them, that's kind of cool, and you can bring them up in an interview, but you're probably not going to need them. You're just going to need the basics that we covered today. I just want to go through this to make sure there's nothing I missed. Like you can see, look at all these trees. We've gone over binary search tree and like a binary tree, right? But there's so many others. Red-black trees, actually. Red-black tree is used for balancing, for automatically balancing the tree, which can be useful in some cases. I did learn about red-black trees in college, but I can tell you since then I've never had to use one. So if you're interested, this is a one that could be fun to look at. Some of these have really funny names too, like what is scapegoat tree? Like why? First case lookup. I mean, yeah, top tree, weight balance tree. B trees. B trees balances itself, but
I've never had a reason to deal with a B tree either. Heaps, we talked a little about heaps, min-max heaps. Most of these, I think min-max is probably the biggest you're ever going to need to get to with that. I've never even heard of bit slice trees or multi-way trees. See, these are a lot of things. Sometimes people just come up with these things because they need to have something for their PhD. People do study this in college. Yeah, sorry, I didn't. I missed that comment because I was too busy just dealing with the sound of my own voice. Yeah, the things that we covered today, those are all things that I went over in that I learned in CS 101, which was just data structures and algorithms. Trees, we had to build them all from scratch as well, which really drills it in. But yeah, people study this in college. They definitely, most college grads that get out of a 4-year university will understand binary trees, hash maps, linked lists, stacks, queues. They will understand those very well. You can get to that same level of understanding. It's not too hard. And that's good because that's one of the few advantages they have over you. And so you can take that away from them just by studying these topics, which I would definitely recommend that you do. Oh, abstract syntax trees. I've definitely worked with these. These are fun. And parse trees. These are for if you're doing code stuff. You build an abstract syntax tree. Hash table. Hash table is probably the only one you're going to need. I never heard of a cuckoo filter. Graphs. Looking at just the basic graph is probably all you're going to need to know. Don't know what any of these. Oh, routing tables are kind of interesting. That's for networking, but that's more like a graph. So yeah, this is a good page to look at. If you just study the stuff that we went over in the presentation, you're probably going to be pretty good. Because if you know trees, then you can kind of understand hashes as well. So let's see. Let's go ahead and take a look at some leetcode, and I want to just show you. We're not going to necessarily do a leetcode. I just want to actually just show you what kind of algorithms what kind of data structures you need for your algorithm, right? Because that's the first thing. So let's look at what we have here. Let's look at one of these. Let's see. I kind of look at a hard one. Merge k-sorted lists. Yeah, let's look at this one. This is a hard one, so I'm not actually going to try to solve it. You're given an array of k linked lists, and each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. So you can see here, we basically have a bunch of lists. They say linked list because if I actually take this into C++, C++ doesn't have the same arrays, so it's actually using a vector here. It's using its linked list. If I go into Java, it's actually using a list node. If I go into JavaScript, we get it kind of easy because we just have a list, right? But they're actually giving it to us as an object. So this is where it comes important. Do you know how a linked list works? This has a val and it has a next, right? This is literally what we just covered in our for our node here. We have a val and we have a next. Well, this has got the priority because it's a priority queue, but this is the same list node, right? And so they're giving us a list of those, an array of list nodes. So this isn't going to be an array of arrays necessarily. This is going to be an array of list nodes, very likely. And they want us to return a single list node. So one way that we could do that is like the really simple way of doing that is just looping over all of these list nodes and inserting and having another linked list that we've created that we're kind of inserting stuff into. Problem is we want it to be sorted, right? And so sorting a list node could be kind of complicated. That's where the issue comes in. We'd have to actually implement a sorting function on this. Or, just do something extremely inefficient. So in this case, if you're going to answer this question, you really need to understand what a linked list is. Not necessarily like, oh, I need to implement the linked list, but you need to understand how it would be implemented because you're going to need to deal with it. As you can see, this list node here, we're going to have to be inserting these, doing next objects on it. Maybe you actually want to do this as a double linked list. Maybe you want to do it as a priority queue. But you're going to have to figure out how to implement it as part of this problem. So that's why knowing these data structures are really simple, or not really simple, really valuable to you. I look at this and I say, okay, I know immediately, I know what a linked list is. So I can tell you, I can already start, like you saw me doing, start to break down the problem of how would I handle this. Because the important thing with any of these algorithms is what is your input and what is your output supposed to be. Now they're saying your output needs to be a list node, which means I need to really understand how linked lists work. Let's look at a simpler one. Problems. Let's look at this one's easy. Palindrome number. Oh, now it disappeared. Is it gonna swatch them all again? Okay, palindrome number. Let's take a look at that. Okay. I think I actually may have done this one before, right? So 1, 2, 1. How it reads is 1, 2, 1 from left to right and right to left. Cool. I know that a number cannot be checked that way. Really, what I want to do is I want to treat this like a list. I also know in JavaScript, a string can be treated as a list. So if I just convert my number into a string, then we're Gucci, right? We're good to go. That's an idea where, like, I know if I'm doing a palindrome, that's basically iterating over an array, which means I need to know how I can deal with an array and how I can deal with a string and how I can deal with a number and how those things all operate together. I think I did solve this one actually in the last one or something similar to it. It's a good one. Let's try to find another. Let's find a medium one. Let's see. Letter combination. Move nth node from end of list. Okay. What is this? Given the head of a linked list, remove the nth node from the end of the list and return its head. Okay. So basically, this is saying, oh, give me the second one, and that's the output. Again, we have to understand how a linked list works because we have to understand how we do this operation. They're asking you to actually code this operation. Now, remember, we went over that in, one of our images, where basically I need to grab, as I'm looping through this list, because I only have a singly linked list, I need to remember what my previous node is so I can hook it up. As soon as I find that nth node, n equals 2, which is kind of, it seems like this n is 2, so 5 then is the head at this point. So I get here, and I say, okay, I know it came before, I need to hook this guy to connect to this one, and then as soon as I do that, the 4 just kind of drops out because the garbage collector takes care of it automatically. But you need to understand that. This is the kind of question. This would not be an uncommon question, I think, to see in an interview or an interview where you need to do something like this. What they're showing you here, this idea of how do I drop something from a linked list, that's something you may need to understand because you need to use this as a piece in a larger algorithm that they're asking you to do. I wouldn't be surprised if something like this hard merge k sorted lists, that might be something I'd ask a junior engineer to do and expect and give them a whole hour to do it. Okay. So, okay, merge k sorted lists. Here's your hour. Go ahead and go over this. What's this little purple? Solution. Okay, I don't know why this is a purple with a check as opposed to, strange. Anyway, yeah, so what I'm getting at is that these data structures, these things that we've covered, so the strict array, you're probably not going to care too much about. Linked list, stack, queue, where's the priority queue, hash map, and the binary tree. These form the building blocks of algorithms. An algorithm is basically going from A to B, input to output. But in order to do that, you are going to get data in the form of one of these data structures, and you're probably going to change it for complicated algorithms into a different data structure so that you can work with it. All algorithms is you're basically answering the question, if I had to get the output, what format would I want my data in to be able to easily get that output? And then the algorithm is pretty much transforming your data into that format. Yeah. So any questions anyone has? Anything in particular y'all want me to cover? I don't know if I don't think we actually have that many people watching. Let me see. Oh yeah, we don't have that many people watching. So yeah, I'll just hold for questions here for a little bit. Drink some water. I was wondering if it's a good idea to learn C++ while doing leak codes in JavaScript. Um, C++ is hard. Is it a good idea to learn it? I would say yes, because it forces you to do things in a way that JavaScript doesn't. And so if you learn C++ and it forces you to do things in a certain way, your JavaScript code is going to be better simply because you've learned a better way of doing things. It's a little more efficient. C++ though is hard. It has a lot of concepts that like memory management and pointer arithmetic and things like that that we don't have in other languages, and there's a reason we don't have them. It's very, very easy to make mistakes in C++ that you cannot make in JavaScript. Like it's actually just not possible to make that mistake. Um, or some of them, like it's very, very hard to make that mistake in JavaScript, and it's very easy to debug, whereas C++ it's almost impossible to debug. Like if JavaScript crashes, you'll get a thing that says, hey, we had an out of memory access bound here at this line, and here's the whole stack trace. In C++, you will get an error that says segmentation fault. And that's it. And you have to hook up a couple of tools to figure out what the hell happened. So I would definitely encourage you to learn any language that you think you are interested in and are actually determined enough to stick with. C++ is a great language to learn. It's just bear in mind it's going to be difficult. When I was in college, C++ is one of the languages we did learn. We had to implement our algorithms in C++. And that was difficult in a lot of ways. JavaScript makes it a lot easier. That same code that I wrote for the linked list in JavaScript, I think was about twice as long in C++. Just because I had to use a bunch of generics and stuff like that. Because C++ is also a typed language. The thing is, it will be valuable for you to learn a typed language. Now, you could learn TypeScript, and I know someone's asked for a video on that, so I'm gonna try to do a video series on TypeScript at some point. Java is also a very good typed language that has its own memory management, so it doesn't have the same kind of terrible horribleness. C++ is a typed language, and so I would definitely say learn it, but expect to be frustrated along the way, and that's not necessarily a bad thing. The more languages you learn, the better off you're going to be, because just the better you'll understand and the more enticing you'll look to employers. If you say, yeah, I've done this whole thing in C++, they're going to say, oh man, this person really knows their shit. Even if it's just a web design or a web programming job, they're still going to rank you more highly because you know more. And they assume that that knowledge is going to be useful, which it will be. But yeah, good question. Good question. Let's see. We got about 45 minutes left. And I could end early, but also like if there's any topic the chat wants that they want me to cover, let me know. If you want me to do some leak codes, we can do that. If you want some more interview stuff, we could kind of go over that. Let me know. Watching the microphone, I can like hear myself swallowing, and that's kind of weird. Or I can watch the sound bar go up. Yeah, you might be right. I think later more people show up. So yeah, I'll put a poll in the server and just ask when people are more free to show up. We'll see. I mean, I could just code during this time too and just write some projects and do some stuff. Um, but yeah, anything in particular you want me to cover? We got a little bit of time. Otherwise, I'll probably end it a little bit early. 238 product of array except self. All right, let's take a look at that. 238 is probably going to be on page 4. No, it's going to be page 5. Ooh, premiums. Okay. 238 product of array except self. Let's see what we got here. This is one you're on now, and you watch the video as prefix. Okay. Given an array nums, return an array answers to answer I is equal to the product of all the. Wow. Okay, the product of any prefix or suffix of nums is guaranteed to fit in 32-bit integer. You must write an algorithm that runs an O of n time without using division. Ooh, that's fun. All right, so basically here, for nums1, we go 2, 3, 4, okay? And that goes 24. Skipping the 1. We hit 2, we multiply 1, 3, and 4, and that goes there. We hit 3, this is 1, 2, and 4, and that becomes 8. We hit 4, and it's 1, 2, and 3 without the 4. This is very interesting. So in this particular case, we got to think about, okay, what do we need? We need an output array. It's going to be the same as the input array. I actually can't think off the top of my head of how I would handle this. It's kind of a fun one. So let's see. All of these are 0 except for the 0. I kind of love that, honestly. I really kind of love that. And then it's actually -1 times -9, which then becomes 9. This is a very interesting one. So, do you want me to actually try to solve this, or do you want me to just give you some tips on how I'd handle it? Let's see, yeah. 30. Pro tips are solving it. So, basically what I would do here, I know I need an answer, such an answer I is equal to nums I. So it's going to be the same length, right? So first of all, I can just start off answer equals, and then I can do this. I'm going to start them all off with the same thing. I'm going to say, okay, you know, nums for I equals 0, I less than, nums.length, I plus plus, because remember they say you must run an O of n time. I'm actually going to do this. I'm going to start off by pushing 0 into all the answers. Okay? Now, I'm like, why? Why are you doing that? Well, because now, what do I have? I have my list of answers. They just don't have the right element in them. I can't use division. Okay? And so there's a couple solutions that could use division. They're like, oh, you can't use division. You can only run O of n time. Now, the brute force, right, would be to run over this n squared times. You have your thing in here, and you say, like, okay, let's just add up all the numbers minus that and just multiply them all together. You don't have to do that. So what I want to do instead, I've got this 0 here, okay? And, oh no, I'm realizing what I want to do is not actually going to work the way I thought it did. Answer that push. Actually, never mind. I was thinking, like, basically the way I was thinking about going about this is every time you go over a number, you basically multiply everything by that number, but that's actually n squared. I'm realizing, because you'd have to loop over answer every time. The issue is that all of these previous ones have to be already stored in the answer array. That's kind of the problem, because when I get to this one, I need to already have 1 and 2 in there, because then I just grab 4 afterwards and I'm fine. But these two I already need to have 2 in this position. So something we could, well, let's see. The other thing we could do is we could kind of keep, well, no, because they don't want to do division. What we could do is we could, for every time we go over this number, we know this starts with 1, right? Oh, no, because then we have to push that in there. Every time you multiply the left indexes to the right of that index. Where'd you get to that? So you're saying, like, once you get to index 3, the thing is, if you're on 2, you do 132. So, like, here, yeah, that could work, possibly. Yeah, this O of n is the interesting constraint. So, like, if I don't have this constraint, what I do here is I would actually loop over twice. I'll just do this without the constraint first, so that we can see. Because doing O of n is always complicated. So for nums.length, basically, I would loop over let j equal 0, j less than nums.length, j plus plus, and then if I does not equal j, nums, oops, this is the answer, j times equals by nums I. Okay, and what that's going to give you, that should give you the answer, I think. Because basically, if I hit this first number, okay, I'm pretty much going to multiply. Well, you know, that's the thing, because this starts off at, if I start them off at 0, that actually isn't going to work because of the multiplication thing. But let's just start off at 1. That's probably not going to be too terrible. I think that'll work. So basically, I start off with a bunch of 1s. I go through and I say, okay, first one, I multiply them all by 1. So these are all 1, except I leave the first one out. The second one, I multiply everything by 2, except for that second one. So now I've got 2, 1, 2, 2. Everything I multiply by 3 now. Okay, I need to write this down because I'm getting lost on what I'm doing. So I start off with 1, 1, 1, 1. The first iteration, I actually end up with 1, 1, 1, 1 because it's all 1. The second one, I end up with 2, 1, 2, 2. The third one, I end up with 6, 3, 2, 6. Okay, and then the fourth one multiplies by 4. I end up with 24, 12, 8, and 6. So this will work for this algorithm. Okay, but this is also n squared. So I have to somehow pull out this guy. And probably they don't want you to use division is the problem. Because otherwise what you could do is inside this thing, you could increment a counter and say, like, oh, at this certain point, we have this counter here and do a bunch of complicated operations with division, but they don't want you to do that either. So let's see. Could we use a hash map for this? Because a common way, if we can get rid of one of these loops, right? That's a common way of handling something. So if we already have the answer, let's see. Can you solve the problem of 1 extra space complexity? If it is not, count as extra space. Maybe, probably not though. I'm not that good. So j0, j nums length, j plus plus. How do we get rid of this? Okay. How do we get rid of this? We need to be able to, and we can't loop over the array, which is the problem, right? That is actually kind of a problem. Let's see, could we start? No, because if we start off, we could start off by saying, you know, this is going to be nums of 0. And just, this is, if we get rid of this array somehow, this is still O of n. So we could start off by seeding our answers with the first number, right? Except for the 0. But that's kind of a cop-out, honestly, because that doesn't fix any of the other ones, and like we can't do that multiple times. We know that our nums are going to be between negative 30 and 30, and we know that there could be a lot of them. The product of any prefix or suffix of nums is guaranteed to fit in the 32-bit integer. So basically what they're saying is that it's going to be 32 bits regardless. That we probably could use, well, in JavaScript we don't actually care about that as much, because we don't have real type issues with that. That's more of a thing like where if we need to deal with Java or C++, they're saying, hey, you could use a standard integer for this. So let's see. Let's see what we can do here. First of all, actually, let me just see if this runs over. I want to just see if this runs over the examples they give us. Because if this doesn't work, yeah. So that works over those two examples. So answer that push. How do we do this? So if we loop over the first one, right? We need to apply that forward, but also backwards is the issue. Okay, so maybe what we could do then is we could have a rolling pointer. So if we do something like this, so let's say if we have a rolling pointer, right? We start off with our array, our answer could actually just not exist at this point. We start off with front of 0 and back of 0, okay? So when we look at our first number, right, we add back, we add it to 1, okay? Or sorry, we put it, well, our front is now completely 0. I guess that's the problem. We need to know all this information ahead of time, which we don't have. Well, let's just do it going forward, okay? Let's see if we can get it going forward. So, we look at our, well, no, because that would be the division. So we get this 6 by going forward, and we get this 24 by going backwards. So if I basically loop through the array once, adding on the front, I would start with 1, okay, and I'd ignore the back. The next one, I would turn this, this would become 2, and this would become 2, okay. The next one we loop to, okay, the front we would add 3, so that would go to 6, and then the back we would multiply by 3 also, and so that would go to 6. And then we go to this one and we skip that for the first one, but not for the back, so we go 24. And so then this gives us our 0 and our 1. So that gives us 24 and question marks and 6. So that is, if we do that O of n, and we just add up like that, that can work for here. But then these middle ones becomes the problem, right? How do we capture those? Now, what we could do for those is we could have another set of front and back that starts after here. Now, that only works. Now, here's the fun part. If I'm breaking these up into pairs now, right? So I'm saying, okay, 4 and 20 and 6, right? Or 24 and 6, we get that front and that back. And we know immediately how to apply those. So let me just try that. Because it might not be clear what I'm actually saying. So I want to loop here, and I want to say, okay, that front equals 0, that back equals 0. Let's actually just set them to 1 for the hell of it. And so as we march through the nums, we say, okay, you know, if I equals 0, then we're going to add it to the front. We're going to multiply nums I. Well, actually, let's say if it's not equals to 0, then we're going to add it to the back. Multiply equals by nums I. Okay. And then, and I'm going to set these to like that. Just so that it's very clear when we've done something wrong. If I does not equal to nums.length minus 1, so we're not at the end, then our front multiply equals by nums I. Okay. Then at the very end here, answer of 0 becomes back, and answer of nums.length minus 1 becomes front. I just want to run that and see what we get. Because I think if we can solve the first two, then we might be able to iterate in. Oh, length is right, because that should be that. Let's see. Okay. Okay. That's fine. Not a number is fine. Completely fine for that. In fact, maybe I actually want to do nan. That's okay because we got those first two. Those are correct. And if I look at case 2, I also got the correct numbers. So in this particular case, what I almost want to do then, the problem becomes then how do we, because if I can iterate over this, I have that front and that back, right? If I can do multiple pairs of fronts and backs, then that could work. But the problem is that also becomes n squared. So when we get to that second one, we know it's come behind us. Let's see, I guess. Yeah, because I'm trying to think, like, how would we handle that? It becomes, we basically want to be able to, maybe we go through the array twice. Like maybe we go through it first and see some data, then go back through the other way. Because I think this can work, right? Front and back, this does seem to be working, right? And so what I want to do is if I just do this for the back, right? If I just do this for that back, it gets that first element and it runs through that. But I somehow want to be able to derive that off of here. Like back, okay, so we have the back of 1. Front answer is 0 is back, okay. I wonder if we can use subtraction somehow on this. Because we know the only difference between, because like if I can do an array maybe of like what this, no, they don't want us to use division though, that's the problem. Because division, we hit this, we know we have this number now. So this number is going to be that number divided by this, but it's also going to be, yeah. Wow, this is a good one. The video you watched did 2 arrays with fill and left. Yeah, two arrays does kind of make sense. Because the first array would actually contain your full answer, and the second array contains some sort of like helper data that gets you to that answer. I wonder if we could, no, because if we bit mask, then that's still an O of n operation. Let's see. So we got our answer. So they just filled. Yeah, I imagine that's actually a thing that you can just say fill. I don't fully know that library method though. Okay, so now we've got that first one. We know we can get the first and the last. We can't really necessarily iterate on that because that would be not what we want. Okay, 24. So how do we get this 12? Because if we figure out to get the 12, we can figure out to get the rest of them. So we have this back. If we use this one value, what happens if we just push the value of back into that? Push back. What comes out of this? Wow, okay. No, I don't. Every time I click save. Let's see. If we just find the value of what that pointer is at every time. Okay, it's 1, 2, 6, 24. Okay, so that makes sense. So we've got the 2. Okay. What if we go the opposite direction as well, right? What if we go, let's call this from front. From front, and then this is going to be from back. And then I'm going to call this counter, just because I want to make it a little bit more generic. And then counter equals 1. Then I'm going to put counter in here and counter in here, and then we're going to go the other direction. Minus 1, I is greater than or equal to 0, minus minus. And then, oops, log from front. This is basically the double pointer method of doing this. I'm just looking at like what do things look like as I approach it both directions, and is there something intelligent about that I can do? We're going to take that out. You may have attempted to code too soon. Oh no, attempted to code too soon. Not me. All right, so we start with, this is the from front. 1, 2, here 24. This one starts with 4, 12, 24, and 24. So it goes backwards and doesn't actually change with that. So, I wonder then if we move, this is the third element and this is the fourth. But 6 isn't, oh no, 6 is in there. We do have 12, we have 24. We don't have 8 anywhere though. That's kind of the problem. Yeah, so that's this issue. So we still have the ability to get the front and the back, which we always had. We just cut off the ends of these, and that's going to be the front and the back. But then I wonder if we multiply, but that's looping through that again. Yeah. What we kind of want is we want something that like has, no, because we know it's 24. This one might be interesting too, whatever we get here. Okay, so that's 1, 1, 0, 0. Yeah, this one's just kind of funky. Because these are all zeros except for that 9 in the end. -0. Oh, JavaScript. -0 and +0. They don't behave any differently. They're the same value in some cases. Some cases they're not. So let's see. Now we've got, and see, the thing is, the important thing is this is still O of n. Because even though I'm looping 3 times, I'm not doing inner loops. So that's totally fine. And if I looped over from back and from front at any point outside of this, that's also O of n because either one of them is going to be. So this is a way you can kind of get around that. I can make 10 of these for loops that go over nums.length, and that's still O of n because it's a constant number of n. And that's the important part. It only becomes a problem if you're actually putting it inside the thing. Let's see. From front, from back. So we have it going this way. We have it going this way. We can't use division. A lot of the there's a lot of different solutions I can think of for this, but they're all like involve looping over multiple times, and that's kind of the issue. So we got 24. That's gonna be, and it's not even like completely reversed. Like you can't just take the sums up here and reverse them and you get that output because it is specifically all this except for this. And you can't use, you can't, this is actually gonna be really stupid. We can't use division, but technically we can use a loop and subtraction. So, again, this is going to be really dumb. But I think, I don't know if I would actually submit this in an interview, but I think it might work. So let's try this. Counter is the nums, right? So we have our full counter, right? I'm going to take this here and I'm going to say, okay, let's loop over. Well, let's just preserve this for now. I'm going to loop over our nums again. Okay. Now, here's the thing. We know what our sum is, right? We know what our number is. Num equals, okay. Nums of I. Now let me think about this. This is going to be answer I, bracket I is going to equal whatever our answer is. And I think, let's set our answer to equal counter. Let's see here, because this is basically that sum divided by 2. Oh, but I can't use division in it. Never mind. I thought I had something, but I didn't. These are also technically pairs, aren't they? Because oh no, but 8 times 6 doesn't add up to 24 or go up to 24. So that doesn't work either. Because I was thinking like if we had some way to do subtraction, but then a certain number of times that also becomes division, but we wouldn't know how many times to do that subtraction unless we're using division. That's kind of the issue there. But maybe we could, because technically the 2 needs to yeah, actually, if we use from front, so we've got our front here. This tells us what we want to get to. Or this, I don't know, the from front here is here. That doesn't tell us much. But does it in reverse? That doesn't tell us much either. This kind of, basically we need to figure out. Yeah, so I know this is, you're probably just like, what the fuck is Robert going on about? What is he thinking? I'm just trying a bunch of different possibilities in my head and thinking about like how I would go through this. Yeah, this is kind of a nasty one. Without either one of these requirements, it's not that hard. But with both of them, it's a pretty difficult one. So what data do we not have that we could possibly get? We know the increment, right? So we have our 1, 2, 6, 24. And we kind of know it from, we know our sum, right? We know the maximum this could possibly be, which is going to be our first, well, no, it might not be our first element actually. So we do kind of know what that becomes. This one is actually a little bit, no, it's not that easy to solve. Got track over it. Yeah, this is always the question, like what kind of data do we need and how could we possibly, like what could be useful to get out of it? Like I'm thinking like could we use a tree for this? What would that give us, right? That would just introduce a log n search, which isn't that helpful. What could a hash map could give us something maybe. So if we know how to build the hash map, we could look that up instantaneously, right? So that could give us a lot of helpful stuff. But what do we put in a hash map? We could build, because yeah, what do we put in the hash map that I'm not already doing here? So we've already got some data that's kind of useful. I go over that. I've got that. The problem is the problem really is like, how do I get these inner ones? The outer ones we've solved. We know how to get that. The answer you found is left of array multiplies right of array and store the answer. Kind of correct. Use 3 of those consts for loops. That could be interesting. Left of array. Yeah, because that's the thing. Like, what is to the left? What is to the right? That's kind of what this front back is supposed to be, right? Left array multiplies right of array. Okay, so I see what you're saying. So to get this first one, we multiply. Left array versus right of array. Yeah, so we could have what is everything on that left. Counter. That's not particularly. I'm gonna pull this out here because that needs to be in there. Yeah, that's kind of interesting. Oh, the output is all 24s. That's funny. Well, that gets that. Left of array multiplies the right of array, right? Okay, so on the left, it multiplies by the right, and then store the answer. Left, right. Yeah, I can kind of see how that would work. So basically, we have, okay, const from left. Let's just call this left. Left, and then, so then what does left give us then, though? So we start off going from the left. At the end here, we want to have all these. But at certain points, we want to have ones with that taken out. So, I mean, we could probably do that with, yeah, I think I kind of see how that would work. I'm just having trouble translating that into the code, to be honest. Okay, new array, numslink.fill. So you're creating an array. Okay, so you're just filling an array with zeros, and you set the start to one, right? That makes sense. That makes sense. And then you go all the way to the right. It's weird that they're doing right.length equals 1 because you wouldn't need to do that. You could just reverse it. But that's okay. Okay, so you're making, I'm just going to put this code in here. Okay, so basically we've got something like, let's just call this something like this. That's right, equals. Okay, so now we're basically creating new arrays that are the same size, and we're setting our left and our right. And, so then, I equals k left times right of I. Let's go through. Okay, so what would that look like? Let's take a look. So we start off with 1, 0, 0, 0, 0. Okay, and the other one is going to be 0, 0, 1. All right, so then if we look at our first element, okay, then we're like, all right, number of I, or our answer, we're going to start off with all zeros here. So our answer starts off as 1 by 0. See, now that's the thing that's a little weird there. If we're multiplying left by right, unless we're filling these up somehow. So let's say theoretically we're filling these up by doing the multiplications across. No, that doesn't make sense. I can kind of see like how you'd take these pairs and multiply them together, but I'm not completely sure how you'd fill these is the issue. That's a tricky one. You know, I would say personally, if I had this interview, and I was taking this interview, I would do it either without the O of N or with the division, just to get it working and get the algorithm all set up and working, and then I would talk through my thoughts like I've been doing for the last half hour, and just see if anything clicks. But that's kind of the best you can do in some of these situations. You can see a couple other of these that I've done that or like a couple of the leetcode videos where I'm just like, I don't know how to solve this, but I'm just going to talk through it. Anyway, let's see. We got our left, we got our right, and then nums.length. Like, what would we fill with those? What would we fill this with? So the left, if we're using 3 loops, these must not be the same loop, because if they're the same loop, we could do left and right at the same time. Probably one of them's going the other direction. So here's one. Let's just set up one going the other direction as well. Minus 1, I greater than 0, minus minus. So now we have, this is probably the left, and this one is for the right, would be my guess. So what do we put in there though? Because basically, if we're at some point doing a third loop, right? That's just gonna go in here and say, oh, is it minus 2? Yeah, I've got the I minus minus on there. So you probably can't see that very well. Let's make it a little bit bigger. Minus 2. I don't know about that. But we're gonna say nums I equals left I times right I. Yeah, and so that makes sense. So then left, so then what that means then is this value somehow needs to multiply up to 24. This value needs to multiply up to 12. This one 8 and this one 6. So left and right Let's look at that then. What could be the possible combinations? It could be 12 and 2. It could be 4 and 6. It could be 8 and 3. So how would we get either of those? Could we get either of those out of that? Well, the 12, coming from the left, getting 12 in this slot, we're probably not going to get it there. From the right, getting 12 in that slot, we could do. Maybe if we're skipping that 1, but that does end up being 24. Or it could be, yeah, I guess it could be 24 and 1 also. So that does kind of make sense if we're just saying this multiplies and this multiplies going the opposite direction. So if we do that, that's kind of what I was doing with the front and back though. Then we'd be saying left I equals left of like I minus 1. I'm just going to put a counter. 1 equals counter times, let's just say counter. Counter times equals to nums I, and then left is counter, right? And so that gives me that. It's not log right, return nums. And let's just see what comes out of that, just to make sure that shows up correctly. What? Assignment of constant variable. You know that's completely fair. That is completely fair. All right, so what did I get? I got this, right? So this is my 1, 2, 3, 4. So that's fine. That's all right. And then this one might go from the opposite, but then what I'm going to say, okay, we're going from I at the end. Let's do our counter equals 1. Same thing, right? Counter of nums I. But then I kind of want to do the opposite for the right. I kind of want to start it on the other end. So I'm actually going to say, what is this going to be? Nums dot length minus 1 minus I equals counter. And let's just see what that gives us. All right, so that gives us something kind of weird. It starts off, that should definitely not be oh, because it starts off the other end, right? Right. And that gives me something that is not completely what I want. So maybe if I just don't do that and I just say, let's try that. I don't think that's going to work though. I think this needs to be reversed. What if I just do that? Because this gives me 0, 24, 12, and 4, which is a little weird if I think about it. Because that... Yeah, so this is... I think the left is... Well, maybe. Let's see what this does. So this is... Yeah, so basically this needs to be 24 or 1, 12 and 2 for one of these two. And so if I do this, this is 24. The second one is 12, which is going to be 4 and 3, 2 and 6, or 1 and 12. So that means in order to make that work, let's see, how could I get that? I don't think the 8 and 3 is going to happen. That's a little strange, though. That is this. The 4 and 6 is that, so that's kind of interesting. This is almost, if I put it in a slightly different order, okay. That's the answer to this, but I think that's because this is an increasing series. I think that's not because of anything in the algorithm. But these are basically all the factors of 24, which is very interesting to me that that's that case. I don't think this is that case, though. I think this one would not follow that. So, assuming that we know we can get probably 1 and 24 here, right? But I don't think that works for the next one. 2 and 12. Because if we had that, we basically had the answer in our right, and like that doesn't give us anything. So let's see. This is basically 1, 2, 6, and 24. Okay. Well, already that doesn't quite work for here because our fourth element, or oh no, let's get to that. Our second element here. If this is 2, then this has to be 6. And if this is 1, this has to be 24. And so if I look at my next element here, the 8 is going to be 8 and 1, 4 and 2, or that's kind of it, honestly. And this is 6. So that already doesn't work. We can't get 8 out of that. This needs to be either 2 or 8. So our left is also not correct. You can kind of see how I'm debugging through this and figuring this out. I don't think I'm going to finish this before we're out of time, but I definitely I appreciate you coming up with this. This is actually a really interesting one. But you can kind of see how I'm working through this. It's more manual than I normally do, but I'm working backwards from the solution. I know where I need to get. I'm like, how do I get there, and what do these arrays need to look like for me to get there? Probably another couple. If I looked at this for a couple hours, I'd probably figure it out. But yeah, this is a difficult one. Thanks for bringing it up. But yeah, because I have 2 minutes left, I'm gonna kind of give up on it at this point. Do you have any other? Yeah, and once you figure it out, it teaches you something. You're just like, oh, now I know how to do that. Do you have any other questions? We got about 2 minutes. Oh, we have 4 minutes. I'm looking at the counter, but I'm ending at 12 and I started 2 minutes early. So we have 4 minutes for any additional questions. Yeah, LeetCode's great for this stuff. It really is. It's very good for training you on how to handle this. Very much so. No, yeah, it's unlikely you're going to be building something like this particularly. A lot of what the reason that they train you on this stuff is because they want to figure out how you think and how you code and what you're aware of. When I'm interviewing, I'm not saying the person must finish all the questions perfectly right. What I'm saying is, do I think they know what they're doing? That's really the biggest question I'm trying to ask when giving an interview is, does this person at all know what they're doing? And if they answer that question is yes, I usually move forward with them. It's not it's not the biggest thing. You don't have to finish the question. I've been hired at plenty of places where like I haven't finished the questions, but I've proved to them that I could, because you're right. 90% of the work we're doing, we're not doing shit like this, right? We're building an API. Like, we're deciding where some HTML code goes. It's not this. The thing is, they want to know that you can do this, or that you, even if it took you time, if you could say, yeah, I'm working on this problem, it's going to take me 2 days. As long as they're convinced that you could actually solve it, you've won in that case. That's totally fine. So, yeah. All right. I think we're going to end 2 minutes early then. Thanks for showing up. I appreciate it. And yeah, I'll put a poll in the server to get better times for this, because there were a lot of people last time and there aren't today. So we'll see. Anyway, take care. Good luck, folks.